Right. Good morning, everybody. Welcome to the Institute for Wireless Internet of Things. We're really excited to have you here today. I remember the inauguration of this event. This institute was 3.5 years ago in October of 2019, and that was the time that I started to talk to Tommaso, the director of the institute, and I got this job, which I've been happily working ever after. It's great to be able to have this event again in person this year. We are planning to have this every year, hopefully. We are looking forward to that. Today, we have put together a very comprehensive agenda with speakers from the Institute, research faculty members and researchers and postdocs who are going to talk briefly about their research, giving you a broad overview of what's happening in the Institute. Then, of course, there are a couple of opportunities, an hour and a half during the lunch and also during the dinner for networking, talking with the industry partners who have been kindly accepting to come over in person and joining us. Then in the afternoon, there's going to be one session about industry engagement. We talk about engagement models at the Institute, followed by a panel focusing on commercialization for the researchers who are interested to start the spin-offs. That will be followed by 4 quick pitches from some of the spin-offs who have been doing really great during the past 3 years, the spin-offs of the Institute. And then right after that, there's going to be a more technical session with posters and demos who the actual researchers are going to be out there demonstrating what they have been working on in the past few years. And if you have more technical questions, they will be around to answer your questions. And of course, after that, we'll be welcoming you with a dinner and another networking session. The first talk of the day is going to be a review of the Institute activities in the past few years. Professor Tommaso Melodia, the director of the Institute, is going to talk about what has been happening in the past few years and the vision about what's going to happen next. We are excited about that. With that, I'm going to welcome Tommaso on the stage.
Thank you. Morning, everyone. Great pleasure to be here. Hope you can hear me fine in the room. And I wanted to start this session by thanking those who made today's event possible. First and foremost, Pedram Johari. He has been really taking the lead on making sure that we have a successful event today and organizing all of the event logistics, etc. Sandra Rias, she's been doing the marketing and communication for the event, and I think she did a fantastic job. She's new to our institute. She's been with us for a few months, and Sandra, thanks for your work. And Nico Smith, Nico's been in charge of all of the logistics for this event, and it's been great to work with all of you. And I also wanted to thank Ted Worth for helping us with the industry panel and the engagement. All right, so we're going to talk a little bit about where we are with the Institute for the Wireless Internet of Things, what has been happening, and where we plan to go next. All right, this is our timeline. We're a relatively young institute. We inaugurated the institute in October 2019. There was a little pandemic that started shortly after that. In February, just right before the pandemic started, we signed a memorandum of understanding with the university. We did a number of other things, including launching our Open NextG, which is our first space outside of the Boston campus in Burlington. And we have our industry day today. And there's a lot that has happened during this time. I wanted to spend a few minutes talking about what is the identity of our institute, what are our research plans, and what are our goals in general. We are a research institution. We want to be a leading institution in the world of smart and connected systems, and we want to take the role of being a leading research engine in this space, as well as helping with development of new technologies. We are an educational hub, obviously that's core to our mission. We want to train the next generation of researchers and professionals with interdisciplinary and hands-on skills in this area. We also have the aspiration to be a think tank in the space of smart and connected next generation wireless systems. we want to contribute to shaping and influencing the global conversation on the future of connectivity. And I think we are at a time where our country certainly needs that. It needs thought leaderships in this space. We want to be able to, we want to make sure that North America maintains competitiveness and leadership in this area. We're also a technology incubator. We're generating IP, working with the university in managing the IP. We're generating software, open source software, but also proprietary software, and that is commercialized through spin-offs and industry collaborations. Let's look at the first part of our mission related to research, right? We want to be a leading institution for research and development in smart and connected systems. Today, the Institute for the Wireless Internet of Things is a well-recognized entity within the university for sure, but also outside of the university in the national discourse on connectivity. The Institute has been funded by 12 different sponsoring agencies. I hope I'm not missing any. I'd like to mention certainly the National Science Foundation has been funding a lot of the basic research that happens at the Institute, supporting the work of a lot of our PhDs and researchers. A number of entities related with national security and defense, including the DARPA, the Office of Naval Research, the Air Force Research Laboratory, and other entity. IARPA, the Air Force Office of Scientific Research, the Office of the Undersecretary of Defense, and other entities like the Department of Transportation, NASA, etc. Probably 80% of the funding of the Institute comes from federal entities. There is a significant, non-negligible portion of the funding that comes from our industry partners. And I'm not gonna mention anybody specifically, but we have a large and growing ecosystem of partners for the Institute for the Wireless Internet of Things. I would argue that this is probably the largest ecosystem of industry partners of any similar institute in this space today in the nation, and it's been growing very fast. Our collaborations with industry when we started WIoT were very sparse, and we found enormous value in working with a number of different partners in this space. We find value in terms of obviously having research and sponsored research, but also in understanding what are some of the problems an industry is facing, keeping a hands-on approach, solving real problems, and in general, that feedback loop that you get from basic research to more applied research, and in trying to transition some of these technologies to the field. Also, significant amount of work with small businesses, including companies that have been incubated within WIoT, but also companies outside of the WIoT ecosystem that find value in partnering with us in going after funding, federal funding, and also solving specific technical problems. The faculty, researchers, and PhD students at the Institute are working in a number of foundational areas that include sensors and energy harvesting, wireless communications and networking. That's clearly a very important part of what we do. Data analytics and machine learning, that's an area that has been growing exponentially for us. Security and blockchains, and areas that are related to policy and business aspects of wireless communications. And the idea is this foundational expertise and the interdisciplinary collaborations are they become part of interdisciplinary group that work on specific verticals that include things like the network warfighter, smart oceans, connected vehicles and drones, work related to medical, and increasingly the space internet. Research, there's a number of different projects and active areas of research. I'm just going to cover some macro areas. Next generation wireless is a big part of what we do. 5G, 6G, there's specific strength in the intersection between softwareization of wireless systems, the ability to interact with the spectrum in a fine-grained way, so through spectrum sharing, as well as softwareization of wireless system, and a lot of work also in the more exotic areas that include acoustics, underwater communications, intra-body communications, nano, bio, and quantum. Significant amount of work going on in artificial intelligence applied to IoT and wireless systems. And with artificial intelligence, it's a broad term. Obviously, we're working on a number of problems that are related with inference, extracting information and making sense of the information that comes from sensing and wireless systems, as well as control, creating intelligent systems that can autonomously self-organize to provide bespoke services and to offer services that had not been envisioned before. Smart IoT systems, applications to a number of different verticals that include digital health, smart agriculture, etc. And a significant amount of work on what we call networking in contested environments, working with Department of Defense agencies and other national security-related entities to address problems in contexts where the networking functionalities are being impaired by phenomena like interference that can be intentional or non-intentional and other things. We have a number of academic partners. This is a non-exhaustive list of some of the collaborations that are active. These are with a number of countries, primarily in Europe and Asia. We are signing a number of MOUs with these entities. There is bidirectional exchange of information, as well as researchers. We have a large number of visiting researchers with our group. Some of them are here today, and they make our work more fun and also make it possible for us to get a continuous exchange at the intellectual and human level. We also, and this is something that we're particularly proud of, because it's not something that typical academic groups do. We engage with a number of entities, consortia, and organizations that are really shaping the future of connectivity, both for what concerns industry and what concerns standards and societal impact of some of these technologies. I'd like to mention the work that we've been doing with the NextG Alliance, which is an industry organization that is shaping the future of 5G and beyond, looking at 6G in North America and creating leadership and advocating for investments in wireless. Work that we've been doing with the ORAN Alliance, which is imagining the future of wireless cellular systems. Work with the Open Air Interface Software Alliance, which is creating open source reference implementations for future wireless systems, and many other entities. Numbers, I'm not going to spend a lot of time, but we've grown significantly in terms of numbers, the number of PhD students, the number of researchers, the industry partners, the spin-offs, and the funding that has supported the activities of the Institute in the last few years. Core faculty, these are the people that by virtue of the MOU with the university are affiliated officially with the Institute for the Wireless Internet of Things. They're all doing a fantastic job. I'd like to specifically mention the work that colleague Kaushik Chaudhuri is doing. He has been working as the associate director of the Institute. Josep Jornet has been also a core driving force for our institute, and Josep has been, he will join us. I hope he still wants to do it as associate director also for the institute, and in creating additional. It's becoming more and more work to handle. I also like to mention the work that Stefano Basagni has been doing in advancing our educational offering, and we're going to talk a little bit more about some of the programs that have been created in this space. A lot of other core faculty that have joined us more recently. A large number of research faculty and research scientists. Again, this is something that didn't exist by and large for WIoT or for our groups when we started, and that there is significant growth of this pathway of professional researchers that are working with us without having to teach. Also wanted to mention our entrepreneurship program that has been led by Ted Worth, our executive in residence, and our staff that is doing a fantastic job in keeping us organized and helping us do what we do best. And last, but not least, a very large number of students that come from all possible walks of life, bring us intellectual diversity and human experiences from wherever they're coming from. Our strategic goals, leadership in the pathway towards 6G is a clear strategic goal for us, something we are investing significantly on. It's a strategic roadmap that we've put together that includes a number of foundational topics that we think are going to be crucial in the evolution towards 6G, and that where we think that our institute has significant strengths and can make an impact. One is what we call conquering the spectrum. Conquering the spectrum is the idea of getting to higher frequency ranges with a system perspective. Professor Jornet, we're going to talk a little bit more about that, has been leading the work related with terahertz systems, where we've had some very significant advancements. You're going to see work, presentations, demos in this space today. Open, programmable, and virtualized wireless systems. Future networks are going to be open, virtualized, based on software, controlled through AI. This is a radical departure with respect to how networks have been designed and conceived in the past 50 years. And we think that our group is really putting forward foundational work, and it's recognized for the work that is happening in this space. And this is an area where we've been investing quite a bit and will continue to do that. AI native processing and control, the use of AI for processing, for control, and for inference in networks. Again, this is an area where there is a lot of work happening within WIoT. We believe that this will continue to be an important and foundational area. Flexible spectrum exploitation. Today, by means of softwareization and more flexible and tunable front ends, we're able to interact with a wireless spectrum in a much finer grained way than we could do 20 years ago, okay? We like to say sometimes that we can program the wireless spectrum in a very fine-grained way through software and algorithmic developments, right? We think that there is no good reason why in the future we will have to continue to have different highways with different lanes where each user can use only a specific lane that has been pre-assigned to that user by the government, right? We're going to see more flexible spectrum exploitation, more flexible use of different spectrum bands, more spectrum sharing. And then an area that we're calling, for lack of a better term, connecting the metaverse, creating much tighter integration between the physical world and the digital world, right? Bidirectional exchange of data between the physical world and the digital world with very high data rate, real-time interactions. And this includes applications that we think are going to be foundational, including digital twins, XR, augmented reality, and holographic communications. Conquering the spectrum, this is, again, Professor Jornet is going to talk about this in a lot of detail, but it's going to the terahertz band, 100 gigahertz and up, and looking at everything from a system perspective, from materials to the networking functionalities to policy and regulation. There is, I'd like to mention that there is a lot of exciting work that is happening. This is work again led by Professor Jornet and others in our team, Michele Polese, that has looked at creating dynamic spectrum sharing above 100 gigahertz to enable coexistence between active and passive users on high-frequency spectrum bands, all done experimentally with the Terranova testbed that will also be covered in quite some detail today. The area of open, programmable, and virtualized wireless systems. Open RAN, as I said, is the future of wireless communication systems. We're moving from a world where wireless communications happen through base stations, all integrated in hardware, that with functionalities cannot be programmed and reconfigured, that sit in a tower, to a world where all the functionalities are migrating to disaggregated entities that live in the cloud, that are open, programmable, and virtualized. Open because there's interfaces predefined and agreed upon that enable the disaggregation of the radio access network. They are programmable because they can be controlled programmatically through abstractions that enable the interaction between AI and other forms of intelligence with the network. And virtualized because we will sit in the cloud with virtualized containers. This is a significant departure from existing wireless systems. It also has an important geostrategic and techno-economic value because it will enable a more competitive ecosystem where North American companies can innovate and compete in a way that has not been possible in the last few years with vertically integrated technologies. There's Open RAN is also an enabler for artificial intelligence, and a lot of work is happening within the Institute on working on specifically controlling the Open RAN by means of artificial intelligence algorithms that act on different time scales, controlling multiple devices, and controlling many different learning and control objectives. There's frameworks that have been developed and made open source within the Institute, like the Open RAN Gym framework. There are the only existing frameworks today to develop artificial intelligence algorithms and applications based on Open RAN. Open 6G, I mentioned Open 6G earlier. Open 6G is a research and development center that we inaugurated in Burlington. It's looking at a number of different things, but certainly at open, programmable, and virtualized 5G and beyond networks. It's been funded so far by the Office of the Undersecretary of Defense, but it's an open research hub, open to the entire WIoT community to innovate in this space, and it's specifically been designed to favor interactions between researchers in WIoT, industry, as well as our government partners. And one of the things that Open 6G is doing is working with our partners and collaborators, developing a reference architecture based on open source software for beyond 5G wireless systems that include softwareized radio access networks, open source core networks, all the interfaces that are necessary to connect the radio access network with near real-time and non-real-time rigs, which are the entities, the abstractions that enable inserting artificial intelligence in the network. And then taking this entire software pipeline and testing it in the various testbeds that are part of the WIoT family of testbeds. I'm going to talk a little bit more about that. I also want to mention that Colosseum, many of you know what Colosseum is. And Colosseum is this large-scale data center, which is also considered the world's largest simulator of wireless systems. Is today, with the evolutions in software that have happened in the last few years, the only testbed where you can test, experiment, play with Open RAN concepts and artificial intelligence applied to Open RAN at scale in a real environment with hardware in the loop. Colosseum is also a what we call a digital twin. We'll hear talks about that. It's an environment where you can test with twins of real protocol stacks, right, that are based on open source software and experiment in that space, and also create wireless RF scenarios that represent a real environment. So you can create digital replicas of real environments, this room, for example, in Colosseum, and test with new applications, protocol stacks, and concepts. AI native processing and control, this is also an important area for us. We're part, and this is work that has been led by Professor Chaudhary, and it also includes Professor Ioannidis. I don't see him here, but oh, you're here. Great. There is, it's the NSF AI Institute that is focused on communications and networking, and specifically on edge processing and on using artificial intelligence to create future wireless systems. We're quite excited of this partnership with 11 different universities. We've been working on a program from IARPA called Sisters, that's with, again, led by Kaushik, with Francesco Restuccia as well, really looking at detecting unauthorized signals in secure spaces using machine learning. We think that there's, again, foundational technologies in this space. And I also wanted to mention in this space the RF Data Factory project. This is funded by the National Science Foundation, and it's trying to create, again, under Kaushik's leadership, a really a one-stop solution for data sets related to machine learning in wireless systems. Making data sets available to the community, data sets that are already existing, creating tools to generate new data sets, and creating awareness within the community about the importance of having data sets and making standardized data sets for advancing artificial intelligence in wireless. And then I wanted to mention work that has been happening related to what we call Z-Touch. You'll hear more about this. Z-Touch is an intent-based framework that is looking at optimizing the behavior of cellular systems by providing high-level intents that define the behavior of the network and translating these intents into atomic and distributed control actions based on artificial intelligence. This work has been led by Salvatore Doro, Leonardo Bonatti, and Michele Polese. Last thing that I'm going to mention in this space is the flexible spectrum exploitation. There's a lot of different programs and work that is happening in this space. One thing that I'd like to mention is a project that just recently concluded with the Department of Transportation. Pedram has been working quite extensively on this, and has been looking at creating in Colosseum models of vehicular communication systems and enabling spectrum sharing between different technologies to enable more efficient communications between vehicular systems. I mentioned Open NextG. Open NextG has the ambition to bring together WIoT researchers, all of the facilities that are available in terms of testing and experimentation, our work and our industry consortium, to create future wireless systems, specifically with a look at openness, softwareization, etc. It's 4,600 of space in Burlington, Massachusetts, that is being populated. We've had the first few hires related specifically to Open NextG. It's co-located with Colosseum, with a large anechoic chamber that is in the Burlington campus, and with a lot of other interesting facilities. That's where we think we're going to really advance with professional researchers, our interactions with industry. And we think of Open NextG as really becoming a research engine on the pathway towards 6G, not just PhD students working with faculty advisor, which is a typical academic model, but also having a number of professional researchers that can work with industry, solve problems that are of interest to industry, and really providing the expertise to a broad community. As part of Open NextG, we have recently applied to become an ORAN testing and integration center. The ORAN Alliance is an alliance of 300 industry members that are really providing the technical specifications for Open RAN. WIoT has been one of the first academic members of the ORAN Alliance. We have applied within the ORAN steering group to become an ORAN testing and integration center. That means that we will have the authority to test interoperability between components from different vendors and certifying the interoperability. There's only 2 ORAN testing and integration centers in North America. We expect that this will be approved. It's been already evaluated by the technical committee, which gave a positive approval, and now it's with the executive committee with the board of the ORAN Alliance, and we expect that it will be approved in the next month. The OTIC will be a testing and integration center. It will also help us create a 6G innovation specific to Massachusetts, specific to the Boston and Burlington area, a hub for economic development around Open RAN and 6G, as well as a workforce development engine for Massachusetts by providing testing and integration capabilities. The architecture, the OTIC will be based on Colosseum, as well as all of the other testing facilities, and the architecture, the software architecture that is being developed in this space. We think we want to continue to be a leader in experimental wireless. Clearly, there is a lot of foundational research that happens here, but we take very seriously the experimental evaluation as well as progressing foundational technologies from conception into proof of concept and potentially advancing them to become technologies that can be adopted in industry. Colosseum, as I said, many of you are familiar with Colosseum and its capabilities. It's the world's largest simulator of wireless system. It has 25 racks of equipment, including 256 software-defined radios, significant GPU, FPGAs, and computational power. It can today emulate at scale with tens and probably a few hundreds of nodes, wireless systems with real hardware in the loop. It's a unique facility, and we will continue to grow Colosseum. We've been going through significant hardware updates and expand the capabilities, making it more flexible, and we'll hear a little bit about that today. Arena is the lesser-known, younger cousin of Colosseum. We can say it's designed with a similar philosophy of software-defined radios connected with antennas through coaxial cables. It's fully programmable. It has 64 nodes that can transmit at sub-6 gigahertz frequencies, and it can be used today to instantiate 5G base stations, 5G UEs, as well as Wi-Fi technologies and things like that. Terranova, again, a quite unique testbeds that you'll hear more about today. It is the only existing testbed that can transmit at 1 terahertz in the academic community. And it also has a very large number of nodes to transmit at various other millimeter wave frequencies, 120, 240 gigahertz, etc. XMILI, this is a relatively new project led by Professor Koutsounikolas in the group. It's creating an open and programmable 5G and beyond wireless platform that is based on the NVIDIA physical layer integrated with layer 2 and layer 3 from open air interface, as well as a large number of functionalities related with ORAN, RAN intelligent controllers, the ability to control with AI. And I also want to mention, again, our role in the power program. Our group has been, from the beginning, part of the Power Project Office, leading it together with US Ignite, a nonprofit in Washington, D.C. It's been a great partner in the Power program. Power has put together contributions from the National Science Foundation, over $50 million, and from a consortium of industry players to create 4 city-scale testbeds for advanced wireless research. These testbeds have today been selected. They're up and running for the most part, except for maybe the latest one that has been selected that is not generally available. They provide a suite of diverse testing platforms, for the most part remotely accessible, that can be used to experiment with future generation wireless systems. And that's something that has clearly had a very important role in our developments. The last 2 things that I wanted to mention in terms of testing facilities is our UAS test range in Burlington, as well as the anechoic chamber. These 2 entities are part of the Innovation Campus. They can be rented by any partner that is interested in using that. And there is an ecosystem of researchers on the Burlington campus and groups that can collaborate on different programs and ideas. Because of all of these testbeds are designed with the same philosophy of softwareization on top of programmable hardware, a lot of what we do on one testbed can be replicated on different testbeds. So in a number of situations, we can test at scale on an emulated scenario with Colosseum, take the same experiment and then run it in Arena in a real wireless environment, and then move again the experiment on one of the testbeds of the Power program, for example, right? To test at scale with the capabilities from the testbeds in Power, right? And this is, again, something that through the Power program we've been promoting as an approach to experimentation in wireless. And we think, especially now that we're moving to a world of artificial intelligence, it will have a significant impact. We need to be able to collect data from different environments and to test at scale in different environments. We're also one of 4 nationwide FCC innovation zones. So for all of the frequencies that you see in this chart, both in our Boston campus and in our Burlington campus, we can obtain experimental licenses from the FCC with a streamlined process, where the government has 2 weeks to answer whether we can do a specific experiment. And this is something that we're finding extremely valuable in a lot of our partnerships and work. So far, don't tell anybody, but we've never been denied the opportunity to do an experiment in one of the frequency bands here. So it's working very well. There's also, I wanted to mention that with some of the testbeds that we have, and specifically with Arena and XMILI, we're now running a couple of these networks as private 5G testbeds that are pretty much open and always up. It's almost a semi-production level. So our researchers can connect with specific phones with eSIMs to these testbeds. So we're going to be continuously collecting data and be able to experiment with all of these. And I think these are the first end-to-end automated testbeds, which are ORAN based, all softwareized, all automated, with the ability to test at scale in a real environment. I said that the second part of our mission is education. We're obviously, that's something very important to us. We have what we call a K2Gray vision to education that includes a program that will be offered from pre-college level to college and post-grad and lifelong learning. A lot of these programs are being developed now and will be offered soon, and Stefano Basagni has been leading all of these efforts. We also have new educational programs, and I again wanted to acknowledge here the work that Stefano Basagni and Giuseppe Giornet have been doing in putting together these new programs. We have a new Masters in Wireless and Network Engineering and a new Masters in Internet of Things that have been approved in the past year. They will be offered for the first time starting in the fall now, and they've had a very good response. We expect a significant cohort of new students starting with these programs in the fall. Part of our mission, influencing and shaping the global discourse on connectivity. We've been working in the past 3 years with our great partner InterDigital and now with 6G World on the 6G Symposium. It's been the first event that talked about 6G, the bringing together, and we intentionally didn't want it to be an academic event. We wanted it to be an event bringing together thought leaders in academia, industry, and government in starting to think about what 6G will look like, what are going to be some of the challenges, how are we going to convince governments to fund 6G at the level that we need to maintain North America competitive. And it's been a great success. Maybe even thanks to the pandemic, the first edition had literally thousands of people registering for the event, and this has continued in the following year. Now there is also a European version of the 6G Symposium. The 6G World is running with other universities. And we've been working with a number of different entities. And again, I'd like to mention the NextG Alliance in advocacy for 6G and for techno-economic competitiveness in this space. There's going to be a breakfast briefing on Capitol Hill. In fact, tomorrow, we're going to participate and provide advocacy for investments in 6G. And a number of events that a lot of the people that you see in this room have been working on and participating. I'm not going to cite all of them, but we're going to have the first IEEE ComSoc school on 6G over the summer. And this is an exciting event. It's attracting students interested in 6G from all over the world. And it's going to be a very, very interesting event. Technology Incubator. We are taking this very seriously, and this is an area where we think that there are great opportunities to grow and work with our partners and create exciting opportunities. There's a few spin-offs that have been created. You'll hear from some of them later today. Some of this, there's a significant number of patents that have been either issued or that are pending, that have been generated by activities of WIoT researchers, faculty, and students. And we work with the Center for Research Innovation at Northeastern to either create spin-offs or to work with our industry partners to license the technology. We have plans for expanding our footprint. As of today, there is a significant part of our activities that is based in Boston, but we have a space in Burlington with our Open 6G campus. We have activities in Portland at the RU Institute. Francesco Restuccia is there with his group, and we expect that to grow in years to come. And we are also planning to expand in the global network of Northeastern campuses, and specifically in London and in Auckland, with a focus on the metaverse. While plans for all of these are still in flux, this is something that will happen, and the university is serious about its vision of creating a global university that is not anchored to the Boston campus exclusively. And as WIoT, we're embracing this vision, and we'll make our strategic moves to expand in a way that is coherent and synergistic within our integrated network of campuses. And that's pretty much all I wanted to cover. You'll hear a lot more today about some of the activities within the Institute. And I appreciate everybody being here. Hope this will be a fruitful conversation. Thank you.
Tomaso, for the great presentations. During the talks today, we may have a chance for one single question per presentation, given the limited time. So please feel free to raise your hands if you have any questions for the speakers. And if there's not enough time, we're going to be around for the networking events to answer questions. Is there any questions for Tomaso right now? That's a great answer because we are limited in time.
I think there are too many questions. People are shy. We'll have the breaks for that.
We have all day to talk. So,
Exactly. All right.
Thank you.
Great. With that, we're going to have our first faculty speaker, Francesco Astuccia. He's going to talk about artificial intelligence and machine learning for wireless and wireless for artificial intelligence and machine learning. Francesco,
you need your mic.
All right. Good morning, everybody. Thank you for coming. Thank you, Pedram and Sandra and everybody else for organizing this. So I want to start with a question. So why do we need AI for wireless and why do we need wireless for AI? Okay. In order to understand this, we need to consider the applications that we want to enable. So if we think about the metaverse and applications such as smart vehicles, what do these applications have in common? Okay, so these applications have in common that they will depend on computing. So they will need to execute artificial intelligence machine learning algorithms to perform tasks such as image segmentation and object detection and things like that. But also they need communications. So they need ultra reliable low latency edge connectivity because they cannot execute all the computing on the mobile device. Otherwise the battery is going to exhaust pretty soon, right? But where does the cooperation between AI and wireless come from? So in order to understand that, we need to really understand the context in which we're operating. In particular, we need to consider the physical, performance, and policy limitations that affect the current systems. And so only then can we understand why we need AI for wireless and wireless for AI. Okay? So policy context. Let's take a look at the mid-bands. Okay? As you know, the mid-bands are becoming extremely congested and extremely expensive, right? If you take the bands between 345 and 444, we have that between 2020 and 2022, the FCC has released about 30,000 licenses, about $3.5 million per license. Not good, right? So you can say too expensive, controversial, because you all remember, for example, the controversy between the radio altimeters and the C-band. So expensive, controversial. Let's go to the upper bands, okay? So, and we see that in the upper bands, for example, upper 37 to 47, we have the situation improves only, $530,000 per license, okay? So it seems that we've solved all our problems, right? Let's move to the upper bands and forget about the mid bands, right? Not so fast, right? Physical problems, physical context. What are the challenges in the upper band? You know better than me that when we go to the upper bands, we have limited coverage, given that by the increased path loss, we need to handle blockages, and we also need to perform beam alignment. So all of these very complex problems. So you may say, well, at least we don't need things like MIMO anymore because we have so much bandwidth there, right? Again, not so fast. Again, if we consider the policy context, spectrum allocations above 100 gigahertz, we see that although we do have a lot of bandwidth, we see that only 8.2 gigahertz are available for with no co-primary allocation. Okay, seems like a lot, but let's take a closer look and try to understand why this is not the case. Okay. So if we take a look at the bandwidth that is needed to establish a 1 terabit per second link, because if we go to terahertz, we need to we need to establish this kind of bandwidth, right? So even with a modulation order of 128, we still need more than 60 gigahertz of bandwidth. to establish a 1 terabit per second link. So we kind of do need to use MIMO, right? So, or move to the lower band and still use MIMO, right? But let's try to delve a little bit deeper and understand the issues that involve things like MIMO today. So if you take your Wi-Fi connection, for example, you have your digital precoder, your access point, that takes as input some spatial streams and forwards the spatial streams to the stations. Well, you kind of do need to sound the channel pretty often, right? And that the frequency strongly depends on the movement of the users and how fast the channel changes over time. So the more the users move, the more the channel changes, the more you need to do that. That's overhead, right? Also, you need to send the feedback back to the access point in order to beamform transmission, okay? So just to give you an idea, in your Wi-Fi network, okay, if we take a multi-user MIMO connectivity, 160 megahertz, okay, pretty short bandwidth, we end up with about 55 kilobyte of beamforming report. If we sound the channel every 10 milliseconds, and I'm being very optimistic here, okay, the airtime overhead is about 44 megabit per second. If you do all the calculations, okay, we end up with 8.2 gigahertz. We end up with an overhead of about 87 gigabit per second. Not acceptable, right? And I'm not considering here all the complexity that is involved, all the computation that is involved in MIMO. Okay, so these are extremely fundamental bottlenecks that we need to address, okay, moving forward. To summarize, policy, performance, and physical constraints are compelling us to do much more with much less, okay? We cannot afford to squander resources anymore. And so that's where AI ML can be a game-changing approach, and I'll try to make this point today, okay? You may ask, Francesco, we've had AI since Turing and wireless since Marconi, so why do you need AI for wireless now? Okay, well, I think right now, today, we have the perfect opportunity to use AI for wireless. Why? Well, first of all, we have experimental capabilities that we just didn't have in the past, right? Tommaso talked about all the great test beds that we have in Northeastern. Those are not just to test our solution. Those are fundamental to collect the data that is going to be used to train these algorithms. Okay, so it's not just, oh, we need to test. No, we need the data because these are data-driven algorithms. So we do need the data. It's foundational to the research. And also we have the computational capabilities that we didn't have up until 2-3 years ago. So these two things combined allow us to train and test complex and deep models that were just impossible in the past. So we understand the opportunity, but now let's understand the need, okay? And to do that, I want to tell you an anecdote. So, back in 2018, we were very lucky to be selected by DARPA to participate in the RIFMILS program in 2018. And so when we started, Kaushik, Tommaso, Stratis, and I, so basically we were told by DARPA, look, we give you an extremely large data set of up to 10,000 devices, and you need to fingerprint these 10,000 devices, okay? At that time, the state-of-the-art was 100 devices. So it was 2 orders of magnitude less than what we had at that point in time. So can you imagine, doing all the mathematical formulation and, explicitly model the problem? Kind of impossible. So what we did was to, train convolutional neural networks to, feed signals and try to fingerprint wireless devices by looking at the hardware imperfections in the circuitry of the transmitters, okay? So in other words, AI becomes compelling, extremely compelling, when closed-form optimization and or classification becomes difficult or impossible, okay? So seems easy, right? Take a network, we feed it data, that's it, right? No, right? So what's the challenge? Well, if we take a convolutional network in the computer vision domain, and I feed a picture of a cat, this is my cat Pixie, by the way. So what happens? Well, I'm feeding the image to the convolutional network, and eventually the convolutional network is giving me, with pretty high accuracy, the image of a cat. What's the point? The point is that I know exactly what the convolutional network is doing, what is learning. It's learning in the eyes and the ears and the fur and all these features that become more and more complex as the network becomes deeper, okay? But what happens when I feed signals to the convolutional network? What happens? What about the input size? 1,000 IQ samples, 10,000, 100, right? It depends on the problem, on a lot of factors we found out over the years. What about the impact of wireless channel? The wireless channel, because what I've learned during training may not be the same when I test with other data. And so this is what we have seen over and over again in our research over the years. What about the neural network architecture? 10 layers, 2 layers, 100 layers. And this is extremely important because the more layers I put, the less bandwidth in terms of signal I will be able to process. Right? So these are extremely foundational and important problems that we need to address. Okay? It's an entirely different domain. So we need advanced techniques to optimize latency, energy, and also space of these models. So I want to give an example of how we can utilize these techniques, data-driven techniques, to reduce, for example, complexity and overhead of MIMO operations. So in your, for example, in your Wi-Fi network, you have that, the channel estimate provided by the stations goes through some digital signal processing. I will not go into details about this. And then at the access point, we receive the steering matrix that is used to beamform packets. Okay? The intuition here was, why don't we substitute the DSP computation with a neural network? But not only that, we split the neural network between the station and the access point. So we have a receiver neural network and a transmitter neural network. At the receiver side, we feed the channel estimate. The receiver DNN produces a compressed representation of the channel estimate, which is sent to the access point, processed through the TX DNN, and then we have a reconstructed steering matrix. It's not exactly the original V matrix, but that's the point. That's the point. Because remember that these DNNs, not only they can be used to approximate computation in a way, right? And as we will see, to reduce complexity and overhead. Why is it fundamentally different, this approach, with respect to things like autoencoder? I want to give you an example, a visual example. So if I take an image of a baseball player, right, squatting, okay, and I train an autoencoder to minimize the overhead that I'm sending to the edge, and I train a split DNN. Okay, these are decompressed representations coming out of the autoencoder and the split DNN. What's the difference? Well, the difference is that the autoencoder is paying a lot of attention to the lines below the baseball player, right? And we see that in the split DNN, the split DNN is not paying a lot of attention to them. Why? Because the split DNN is performing task-oriented compression. What the DNN is caring about is classifying the baseball player. It doesn't care about reconstructing all the image. So that's a fundamentally different approach, okay? And that's why, I won't show it today, but we get much better performance than autoencoders, okay? So we collect a lot of data, in a off-the-shelf Wi-Fi network with 2x2 and 3x3 network configurations. And so we have a lot of details in the paper, but I want to bring your attention to this. So we noticed that for a given compression factor in the RX DNN, we get to less bit error rate with less computation than the original 8211 algorithm. So with less parameters and less overhead, the neural network performs better. Why? Is it because of black magic? No, because the key intuition is that in that particular environment, okay, in that particular context, the 8211 algorithm is not the best algorithm from a computational performance standpoint. So the lesson learned here is that tailoring the DNN to the environment and the hardware leads to better results, right? Again, we have the data, we can do this. There are other problems, but now it's possible, okay? The last example that I want to show is how we can optimize the wireless network to execute better AI at the edge. So, let's take as example a smart vehicle application where we're sending tasks, what we call tasks, to the edge. Through the wireless network, we have a DNN executing some sort of classification, okay? And then the result is sent back to the vehicle eventually. So what's the problem? The problem is that if we send high resolution images as they are to the edge, we're gonna saturate the network. So if you throw in some number and 100 kilobyte per image, we do inference every 1 millisecond with 100 vehicles in the network, we end up with 10 gigabyte per second of uplink traffic. Do you think we can afford that with all the spectrum situation that we have today? No, right? Obviously not. So how do we balance the network load with the much needed AI accuracy? Because I have a dilemma here. On one hand, I want to minimize the overhead that I'm putting on the network. On the other hand, I want to have decent accuracy. Okay. So what we did is to approach this problem from a semantic point of view and looking at the data. So again, I want to show a visual example. So let's consider an application when I want to classify objects at an intersection. Okay. So I have this original frame that is about 62 kilobyte. And so I apply the YOLO-X model to classify objects inside the image. Let's try and see what happens with two different levels of compression. So this is about 50% the original frame size. We'll still see that the model is performing pretty well, right? Detecting the person, the bicycle, the car, and with pretty high confidence, okay? But when we get to 2.3 kilobyte, we'll still see all the objects in the background are lost. We kind of the bicycle is lost also. I'm still able to detect cars and people, right? And so that's the intuition. The intuition is that by looking at the nature of the application that we're considering, okay, we can establish a semantic relationship between the application, compression, and AI. You find all the details here. We're going to present this paper next week at Infocom. But basically, the point is that according to the application that I'm considering, so if I'm classifying animals or people or some other objects, I can compress the input more or less according to what I'm actually classifying. And based on that, I can optimize my wireless network to reduce the overhead by considering this amount of compression. Okay, that I'm performing on the input images, okay? So we implemented this end-to-end system on Colosseum. I won't go into details, but basically we compared this to the state-of-the-art, and thanks to the semantic nature of the optimization, we're able to allocate much, up to 170% more tasks than the state-of-the-art algorithms, okay? Conclusions. Wireless networks and AI, they will need to establish a symbiotic relationship in the near future, okay? To survive. It's not a matter of, oh, it's a nice to have. Survival, okay? And again, I think there are many, many exciting opportunities, research opportunities at the intersection of core AI ML, wireless networks, and computer engineering, okay? That's it from my side. Thank you very much. If you have questions, offline. Thank you.
Thanks, Francesco. Our next speaker is Professor Ken Duffy. He's going to talk about next generation error correction decoding. Thanks, Ken. Pointers?
Hello, everybody. Thanks for coming today, as everybody said. It's great to follow Francesco. I want to tell you, at a very bird's eye view, work that I've been doing for the last 4 or 5 years, having recently joined Northeastern as a professor in both ECE and mathematics. Everything I'm going to talk about today has joint work with Muriel Medard at MIT across the river, And all of the hardware that I'm going to talk about was being done with Rabia Yezhizigil, who's in Boston University. We've been working on this project in general for about 6 years now, so there's been a large number of postdocs and students who have collaborated on the project and generated a lot of contributions towards it. The context for the conversation is about what's going to happen with error correction in future networks. In particular, we want to keep in mind the kind of things that Tommaso was mentioning earlier on about how, by opening things up, you can improve the performance of environments. So error correction, encoding and decoding is used everywhere in all forms of data. Basically, any data can be subject to corruption, whether you store it or transmit it. And in order to recover that data rather than lose it, or even to identify if it's being corrupted, we use error correction encodings, which basically takes your data and expands the number of bits that you have to ensure that a receiver or a reader will be able to identify either that something has gone wrong, and then if you're lucky, be able to correct the data. There's basically two fundamental models. One of them is hard detection. This is like you read your data off your disk, and what you find is that something is wrong, but you don't know when that error occurred. The other one is more like the wireless communication, where I mutter when I speak. And because I mutter, you can localize to where the error is likely to be and identify how to correct it. And basically, encoding and decoding algorithms, which have been around since the 1950s but are still subject to development, the way nearly all of them work is they're kind of co-designed. So the way you should think of an error-correcting code is essentially like a perfect mathematical grammar. So what I do is I'm going to speak with some perfect grammar. And then what happens if you receive something and the grammar doesn't check out, what you can do is you can say, well, something is wrong. And the way it works normally is that clever people, knowing the grammar, design rules so that when you receive something and the grammar doesn't work out, you can try and figure out, well, what was the most likely thing that was sent that would be grammatical? That's the way they nearly all work. And the result of that paradigm is essentially you need distinct software for software or hardware for encoding and decoding every communication. It also means you have to standardize. If I'm going to use a single grammar when I speak to you, you're going to have to know exactly what that grammar is, and you're going to have a set of rules for correcting that grammar when you receive it. And so, for example, that means in 5G New Radio, there's going to be two sets of codes that are standardized. One is low-density parity checks, which were invented across the river in the 1960s, which are all for all data communications, and perhaps more excitingly, CA polar codes, which are only 10 years old. And they were introduced because historically in networks, what you really care about is transmitting large volumes of data, ensuring that it can be recovered on the far end. Modern applications of the sort that Francesca was mentioning, like AR, VR, V2X, all these sort of things, they require small amounts of data to be faithfully sent very quickly, right? And what happens is the older structures that people were using were no longer sufficient. So this is what has driven this design, but it still has to be perfectly standardized. You still have to agree what's being sent and what's being received. What we've been developing is something called guessing random additive noise decoding, which has the feature that it's not language specific, if you like. It can take any encoding rule and perfectly decode it. It can provide optimally accurate decodings of any code, including codes for which there has never been an error-correcting decoder for before, including very simple things like CRCs. CRCs are added to every piece of data. So you take a piece of data, you add a CRC, you transmit it, and at the receiver, what you do is you go, if the CRC checks out, the data's okay, and if not, I'm either going to discard it, demand a retransmission, but in fact, you can use CRCs to error correct. We've designed these things so that we can do them perfectly in both hard detection settings and perhaps more excitingly in soft detection settings, because normally with soft detection, that is having some additional information about where the errors are likely to be, normally that makes your algorithm harder to implement and therefore more energy expensive. And it turns out, because of turning a paradigm on its head, we can do this in an even more energy efficient way with soft information. So a natural question arises is, if I can now suddenly decode any code out there, surely the reason we have selected codes for standards is because in some sense they're special and brilliant and excellent. Now, if you know your mathematics in the 1990s, there's papers that tell you if you could decode codes, if only you could, they nearly all would provide the same performance. Now we actually have a universal decoder, something that can decode anything. We can check that. And indeed, what I'm trying to show you here is this is a standard kind of performance metric for an error correction decoder. On the x-axis, I have a measure of SNR, if you like, so signal to noise ratio on a wireless channel. And on the vertical axis, I'm telling you what proportion of the blocks are decoded incorrectly. The outer green line is what happens if you take control channel communication at present and you use one of the standardized decoders, one that was developed in UCSD and is licensed by Samsung and the like. And the green line that's on the interior is what happens if you decode that exact same code except with our decoder. And what you find is we do better. And there's technical reasons for that, which I'm happy to explain if people are interested over coffee. But perhaps just as interestingly, all of those other lines that I'm plotting there, the black line is what happens if you pick a code at random. Literally, no design, you just pick a code at random. It gives you the same performance. You pick a CRC, so one of these CRCs that we're ubiquitously using anyway, gives you the same performance. And polar, the last one, the light blue one, is one of the most recent inventions, which again gives you all the same performance. So it's not like the standardization process has led us to some really optimal scenario where these things are particularly brilliant. Now, of course, I can provide you like a plot like this, and I could have used a supercomputer here in Northeastern to produce these plots or not, so you might not believe what I've done. And we knew that people wouldn't believe us from quite early on, so we decided the ultimate demonstration of the efficiency of an algorithm is to generate it in hardware. So with Rabia, we have taped out 2 chips over the last 2 or 3 years on a very fast cycle. These are die photos of the chips. The most recent one was presented a few weeks ago in ISSCC, and it was the first ever sub-picojoule per bit soft detection decoder. So not only can it decode any moderate redundancy code, you basically, it's very easy. You can load your code onto the chip and it will decode it, but it's also the only published decoder that's actually sub-picojoule per bit. So we can do it very efficiently. And even though we demonstrated this in hardware, the reason why an academic team can create hardware that is more efficient than teams from the very large companies is because the algorithm is really very well suited to it. And it's actually something we can do in software as well. I wanted to mention one of the derisata of 5G new radio had been to provide this ultra-reliable low-latency communications. The traditional paradigm for how you decode an error correction code, as I said, is using special structure of the codebook. So what happens is the decoding algorithms, when they try and find, the grammar hasn't worked out. I've received a piece of data. It's not in my codebook. I want to find the nearest thing. What people have to assume, essentially, when they design their decoder, is that every bit is likely to have been damaged independently, right? So a necessary requirement to be able to send you a sharp alert of data is that I need to use a short code. But on the other hand, to use one of these decoders, I have to assume that every bit has been hit independently by noise. And to square that circle, what people use is massive amounts of interleaving. Essentially, bits that are near each other in the data, when I transmit them, I separate them by large distances, because it's the only way of ensuring that they look like they've been hit independently. So even though 5G new radio provides you with these very short codes, they actually take a long time to transmit because I have to separate the bits in the communication over a distance. People achieve that in interleaving. Interleaving happens everywhere. It happens down in your NIC. It happens throughout the whole thing. Even in 5G new radio polar codes, they have an interleaver inside them. They so don't want any correlation in the decoding. But information theory tells you that's a bad idea. There's information in correlation that can be exploited. The reason why people do this interleaving is if you took one of the existing codes in the standard and you didn't interleave and your channel experienced correlation, what would happen would be the decoding performance would degrade. We'd no longer be able to provide you with the ultra reliable element, right? So they need the interleaving or their decoder is going to fail. What happens if you use the methodology that we've developed is a triple whammy. You can basically ditch the interleaver. use the very fine measurements that my pals in the front row can provide us with about the quality and the correlation in the channel, and exploit them to decode faster, so we don't need the data to be separated, and to decode better. And the reason for this leap in logic is to do with the fact that if I give you a communication and I tell you there's a certain number of errors in it, in the original data, it was nice and clumped. And finding that clump and fixing it should be easier than if I tell you, I'm going to take those clump of errors and I'm going to distribute them randomly. And now you have to go and find each and every one. And that's basically the task that existing decoders have. So this decoder that we've developed, I would claim, is the first one that can actually deliver ultra-reliable low-latency communications, because we can do it efficiently, we know we can do it in hardware, we know we can do it in software, and we know we can do it without interleaving. But given this was to be a 10-minute bird's eye talk, the principle of the techniques that we're developing actually open up a whole large number of other opportunities, revisiting this old problem and enabling technologies that are suitable for new modern applications. And so with that, I'm going to leave with just telling you, if you want to learn a little bit more, at the moment we're keeping a website at MIT that has a collection of all the papers and other information of that sort, and soon there will be one at Northeastern. And with that, I'm going to close.
Thanks, Ken. Our next speaker is Professor Stratis Ioannidis. He's going to talk about robust machine learning at the edge.
So let me join everybody and welcome you here today. Thank you so much for coming. So is this working, by the way? Good, but how do I progress? Next. All right, okay. So let me just start by saying that this is joint work with all these amazing individuals, and you may see them later today at the poster and demo session, so please say hi if you do. All right, so I will be talking about this notion of robustness in machine learning. So the principle here is that if you take a neural network that has been trained in the traditional way through stochastic gradient descent over a standard data set, people have observed that you can take an input that you would feed to that neural network and add some very small, carefully designed, imperceptible perturbation to that input, feed it to the neural network, and make it output a wrong label. Okay, so that's the notion of an adversarial attack. And there's many examples of how this can go wrong and how this can be bad. There's this example of adversarial graffiti where you design stickers that you put on signs, and through this you can fool a self-driving car that is trying to detect these signs. And to advertise Northeastern a little bit, so our colleague Shelley Lin and her group have designed this adversarial t-shirt that if you wear, you can fool face recognition software. All right, so now imagine that we're kind of like building this deployment of ML algorithms on the edge that also Francesco talked about. Then this notion of robustness becomes even more heightened, okay? So because when we're deploying algorithms out there in the field, out there in the open, there's a changing environment, there's the possibility of attacks. So the need to kind of like be able to resist such attacks becomes even more important. Of course, there's other desiderata as well. So if you want to do this, doing more with less, as Francesco said, and you want to deploy such algorithms on the edge, you will need to do it taking into account the resource constraints that devices that you will be using might have. So Professor Chowdhury and I have been working with Professor Yanji Wang, who's an expert, a leading expert in compression of deep neural network models and their deployment in resource-constrained devices. And specifically for this task, this radio fingerprinting that also Francesco mentioned, we can indeed compress neural networks to a great level using far, far more energy and far fewer computational resources while maintaining their accuracy. Okay, so this can be done. There is this desideratum also of efficiency, if you will. The problem is that compression, which usually happens through this notion of pruning, often is at odds with robustness. So let me illustrate this with an example. So suppose that we take a neural network that has been trained to be robust to adversarial attacks. How does this usually work? Well, you basically feed the neural network during training adversarially generated examples, so you solve a mini optimization problem per sample in your data set. Okay, now this is an extremely computationally intensive process. So imagine that you take a neural network that has been made adversarially robust through such training and has been trained by somebody that has far more computational resources than we do. Okay, and this neural network that has been pre-trained to be robust, you want to take it and put it in an edge device that is resource constrained. Okay, so what can you do? Well, you can use one of these pruning techniques that have been developed for this purpose. But the pruning techniques work by refining. So you throw away some edges, you set some weights to 0, and then you retrain. And then you throw away some edges, and then you retrain. So continuously doing this, you finally end up with a network that has good predictive accuracy and is compressed. Well, if you do this and you release it to the edge, then you will immediately lose all robustness. Okay, so this neural network that somebody with more computational resources than us trained in an adversarially robust manner, and we want to take and deploy it on the edge so that we are also robust, we lost all robustness. Okay, so the accuracy against attacks becomes 0 the moment we start pruning. All right, and just to give you a little bit of a teaser of what we can do, we can actually do this, we can actually maintain robustness, and in fact we can do this without any further adversarial training, leveraging the adversarial training that the company that had more resources than us was able to do. All right, so this is kind of like where we are. So we have designed, we accomplished this by using a regularizer, an additional penalty that we plug into pruning, while pruning, that maintains robustness. This is based on something called the Hilbert-Schmidt independence criterion. So it increases the robustness of adversarial training if you incorporate it in adversarial training. But you can use it in order to maintain robustness even without access to adversarial examples. And it also has broader implications for robustness against changes in distribution. That's something that is more recent and we'll be presenting in the summer. Okay, and it also maintains robustness while pruning, and we've also been working on something called communication-aware pruning. I would love to talk about that at some point, but with the time allotted today, I won't be able to do so. Okay, all right, so let me tell you a little bit about how this works. So the idea comes from this notion of an information bottleneck. So this is an observation that people made regarding how a neural network behaves during training. So if I take a neural network here, it's a neural network of 4 layers, and I plot, as I'm doing stochastic gradient descent, as I'm training the network, what is the mutual information of a latent layer with the input, that's on the x-axis, and the latent layer with the output. So here you see all 4 layers, or 4 latent layers, and their respective mutual informations. And you start from the first epoch all the way to the last epoch. So you can see that there's 2 distinct phases. There's the fitting phase, where the mutual information of the latent layers with both the input and the output increase. So we're fitting, we're learning, we're becoming correlated to both the input and the output. And at some point, there's a phase transition. So we keep increasing with respect to the output. So every latent layer is discriminative, is correlated to the output, but it's less correlated with the input. So what's going on there is compression. We're effectively removing redundant features from the input in these latent representations. Through the latent layers. And if you think about this, increasing the mutual information with the output increases discriminative power. It's good. Reducing the mutual information with the input removes redundancy, which is also good. But in some sense, becoming decorrelated from the input also increases robustness. If you're becoming more independent from the input, you are more robust to potential perturbations of the input, and that's exactly what we exploit. Okay, so ideally we'd like to put a penalty we'd like to add that as a penalty while training. This mutual information is notoriously very expensive to compute, so instead we use something called 8-SIC. I'm not going to go into this too much, but in some sense it's a proxy for approximating the mutual information, and you can take gradients over it, you can differentiate, and you can do gradient descent over it. All right, and just to show you a couple of results. So basically, if you do adversarial training, so if you do what I showed before in terms of kind of like training a robust neural network, and you plug in our penalty, so for all these state-of-the-art adversarial training methods against all these state-of-the-art adversarial attacks, you always get an improvement, and this improvement can be quite significant. AA is the strongest attack, and we still get an improvement when we plug this into the adversarial training pipeline. Most importantly, you get adversarial robustness even if you don't use adversarial examples. So here I'm showing the robustness against the AA attack, several attacks, as I'm increasing the strength of these attacks. And you can see that we still have some robustness even if we don't train with adversarial examples, simply by adding this to our penalty. And I'm comparing also here to other approaches of approximating mutual information, including variational methods. So our 8-sig-based method is much, much better. Okay, and finally, what happens if we take so here we took a neural network that was trained by other researchers to be adversarially robust, and then we proved it after adding this to our penalty. And as you can see, basically, so on the x-axis, I'm showing you if you do pruning, you use adversarial examples or not. So if you don't use any adversarial examples, you're super fast. If you use adversarial examples, it can take up to 80 hours in order to prune. We are always the little sort of like a box on the top left. So we have very good accuracy with very little pruning time. And for other methods that use adversarial pruning, if you don't give them adversarial examples, robustness completely collapses. At some point, they catch up if you give them adversarial examples, but it can take as much as 7 times longer compared to us when we don't use adversarial examples to get to the same accuracy. So that's about it. Thank you for your time.
Thanks, Stratis. Our next speaker is Professor Yanji Wang, and his talk is about algorithm software co-optimization to enable large-scale generative deep neural network models on mobile devices.
Thank you. Thank you. So how to go to the next? Yeah, how can I control this? Okay.
If you need a pointer.
Sure. Yeah, thanks. It's my honor to come and present our work on the deep learning acceleration on the edge devices. So I think the future will be somewhat like the ubiquitous AI, that currently the AI is mostly centralized. But in future, that we want to deploy the AI on all kinds of the embedded and mobile devices. There are multiple of the reasons. One is because of the privacy and the security reasons, that the users want to deploy the AI on this kind of devices with privacy preserving. And also because of the latency and the locality, that if we are going to perform the AI on the mobile devices, we can perform in the order of tens of milliseconds or even faster. And also there is a cost and a power requirement that the data center hardware and software is somewhat like saturating. And also because the cloud service is somewhat like increasing rapidly. So we're going to find, so the cloud is becoming more costly, and then we want to distribute to the edge devices. So the AI use cases are exploding, including currently the generative AI and also the large language models such as GPT. But actually, the AI models are becoming increasingly large. For example, like the transformers is actually increasing in the speed of 750 times in every 2 years. But the hardware is saturating because the Moore's law is only increasing by a size of 2 times by 2 years. So the edge devices is somewhat like constrained. They have limited power budget, but then we need to satisfy the real-time constraint. So there is somewhat like a gap between the AI applications with the edge computing facilities. So there is somewhat like a gap there. So the software solutions is needed to fill in this gap to enable the real-time AI performance. So from the AI models, we need to have multiple steps and then go to the final hardware for the acceleration. So typically there is a model compression, and then there is a graph level, the high level, and the low level optimizations. And this is a compiler-based code generation to enable the real-time AI on the mobile. And there is also the runtime optimizations. The runtime means that the dynamic scheduling and also to make it enable to work on the heterogeneous devices with multiple neural networks. So there is problems of the current optimizations that each of the steps is individually optimized. So overall, if we optimize the model, we cannot guarantee it to work on the compiler and on the mobile. If we work for the mobile devices, so we don't know what is the current model's new operators, new structures, and new optimization opportunities. So actually, our work has developed a holistic full-stack optimizations, that it is a cross-cutting code design through all the stages. We optimize from the model to the both levels of compiler code generation and also to the adaptive runtime. So we can get higher efficiency without sacrificing accuracy. We can get about 3 times power saving, 10 times speed up, and in total of 30 times energy saving. So we can enable the next generation deep neural network models, for example, like BERT or GPT, vision transformers like NERV, and currently the diffusion models. So recently, we can enable the stable diffusion on the mobile devices in the speed of 2-3 seconds per one image. So our design is a compiler and compression code design. We have the model optimizer that optimizes model structures with the different types of pruning and the network architecture search. We have the compiler from the higher level and the lower level, including the fusion techniques and the automatic code generation. And also we have the first DNN-driven runtime that is going to have the adaptive power control and the scheduling. So actually our work can work for a large variety of deep neural network models and also a large variety of the chips and the platforms. So it is a full stack and automatic design systems. So showing some of the results, so this is actually featured in the communication of ACM and is announced together with the Turing Award. And then we can see that this is an optimization at all the levels with top-tier publications from the model-based and until the system-based. So we can see some of the results. So on the mobile devices, we can deliver up to 10 times speed up on a broad portfolio of neural network models without degrading accuracy, so under the same accuracy. So we are comparing with all types of the other acceleration frameworks like the MNN, the TensorFlow Lite, and also TVM. And then we're comparing the all types of the models, including classification, until the large language models and the generative AI. So we can see the average speed up is 6.4 times up to 18 times. And then we can see the comparison list here. So we can also see some results on the mobile devices. So it's very difficult to control here. So we can see some of the resolution upscaling demo. So we can see this is the original low resolution video. And then we can see that this is our high resolution. And then this is a high resolution from the TensorFlow Lite. So this is on the device from a lower resolution to a higher resolution. And then the reason is that and then we can reduce the communication cost. We can change from the communication to the computation. And then we can see that our resolution should be higher than the original one. And actually, ours should be faster compared with the TensorFlow Lite version. So we can see another demonstration here. So because of the resolution, so it is not very clear, to be honest. So we can see we can actually enhance the resolution. And actually, we can make it real time. So sorry. So we can see some of the demonstration here, like the instant segmentation, hand gesture recognition, and also question answering using BERT. So we are also the first to support the GPT on the mobile devices. On the large language models, we can accelerate by up to 8 times. So we can support 4 models out of the 8 in GPT-3. And then we can enable this in real time, almost real time. And then for the GPT-2, we can make it 150 milliseconds, 8 times faster than the other frameworks. And also, we can enable this on the mobile DSP, which is actually somewhat like accelerators considered. And then we can also work for the microcontrollers on the Raspberry Pi and also Raspberry Pi systems. So this is a Raspberry Pi. We can see that we can accelerate YOLO by 10 times. And then previously is 1.4 seconds per image. which cannot be real time, and we can make it 150 milliseconds per image. And for the microcontroller, actually it has limited capability, but actually we can accelerate it by 2 times or more. So we can see some of the results on the activity detection. Actually, this is Raspberry Pi systems. So we can see this is our activity detection. This needs to do a detection in every 16 frames. So this is relatively slow. But actually, we can actually recognize in every 2-3 seconds. So this is our somewhat our solution. So this is a relatively large neural network because we need to accumulate over a number of frames, and then we can detect the activity. And also the computing capability is much weaker, about 6-7 times weaker compared with a mobile device. And on the other hand, we can see this is currently the other fastest solution. So this is the fastest solution, MNN, at this moment. Almost the only one that can support activity detection on this kind of Raspberry Pi systems. And we can see it almost requires almost one minute for a detection. And we will see that the detection is also wrong. So I think it will finally give a detection results, and then the result is also wrong. So we can see that this is a difficult task, and then we can do much stronger results. Thank you.
Thanks, Yanji. The next speaker is Professor Kaushik Chaudhary. He will be talking about digital twins for wireless connected vehicles.
Well, thank you to everyone who's here. I realize I'm probably standing between you and lunch. So I promised to entertain you with some nice pictures and of this whole digital world that we now live in, which is the real world as well as its representation in its virtual presence. So this is a car that is going to come back in just a little bit of time. So I wanted to give you a teaser. It's intentionally put as a little bit rough around the edges so that you wait and watch as to what's coming. But this one has cameras and LiDARs, and all that will play an important role in the way your future wireless standard will work. So wireless in the future will not just be RF. So you will not just rely on RF inputs to guide your wireless decisions, but you will use the totality of all the sensors that are actually present. So with that said, I just wanted to say that this work is in collaboration with Debashri, Stratis, Jennifer, and many other postdoc students and faculty who are working together on this. So the first question is, what is a digital twin, right? So you can look at a digital twin in many different ways. You can define it in many different ways. The way that I am going to define this is, here you have a virtual world, and there's where you see this little building where we are currently in, and this is the garage right next to it, and this is a narrow stretch of road on which I'm going to drive an autonomous car. And what I can do is I can replicate this entire environment with some level of fidelity in a virtual world. And in this virtual world, I create these buildings, I create this road, I create these representations of vehicles, but not only in terms of a map or not only in terms of structural similarities, but I can also create a resemblance in the wireless propagation paths. So for example, using software, we can create multiple paths, reflections along these two buildings in a way that reflects very closely what is actually happening in the real world. Now the question is, why would you need that? You would need that because often collecting a real live data set in the field is incredibly complex. Oftentimes you need huge amounts of data to train good machine learning models that will accept all these different sorts of inputs, especially if you have multimodal inputs like cameras and LiDAR and all that, and come up with actionable decisions. So to create those data sets and to test some of these in a more controlled setting, you might need a digital twin, and for that is what you see on the right-hand side. Now, I'm going to give you a use case, and I'm going to show you how this use case is enabled by the creation of the digital twin. So the use case we're going to look at is there's a vehicle moving in a typical urban scenario at typical urban speeds, and it has a millimeter wave radio mounted on it. It is trying to establish a beam with a roadside unit, and that's what you see here on the side. And because these beams are so directional, as I think my colleagues before pointed out, the need for having highly directional beams in these higher frequency ranges, you really need to quickly point and identify which is the optimal direction. So the standard says you should go and sweep multiple sectors and find at both ends which is the one sector where your signal strength is maximum. But what we want to do is we want to use natural sensors that are present on the car, like you have a camera on the car, you have LiDAR, you have a GPS unit, and can you fuse information from all of these different modalities to know, hey, here is the base station, so now let me point there. Or here's an obstacle, and I can't really get to the base station in line of sight, I should probably bounce off the wall. So these decisions can be taken using this multimodal framework that we have designed. Now, just to give you a sense of what kind of operations are we doing. So here is an example of individual neural networks that are operating on an individual modality. So these are all unimodal networks. So this is only operating on GPS or only images or only LiDAR. And it is generating these latent embeddings here, which are then concatenated and then fused together to come up with a final decision on where to point to. So partial processing here and then finally aggregated, and then you come up to a final decision where to point. Now, just to tell you, give you a sense that yes, we have shown this to work in modest settings, but the problem that happens is that if you train this, if you collect a data set in one setting, for example, if you train on line of sight, you do reasonably well in line of sight, but you don't do too well in non-line of sight conditions. So this is an actual data set in an actual car, right, collected in a real vehicle. Similarly, for non-line of sight, you do well with non-line of sight, but you're sort of failing in the line of sight. So you see this drop in accuracy. This is the problem because I don't have sufficient data. I haven't collected enough data in the live world to convincingly say that it is going to perform well in all possible conditions. So for that, I need a digital twin where I'm going to replicate this environment. I'm going to train my models in that environment, and then I'm going to take the trained model and then test it in the real world. That is going to be the thesis of what I'm trying to do here. So, in this, I'm going to take this whole problem one step further. My colleague, both Stratis and Francesco, told you about this whole interaction between computation and communication. Now, a twin, in a sense, is a computation engine. It is replicating this world. It is creating these rich multipath effects. It's creating rays that bounce off buildings and vehicles and whatnot. So to do all that computation, you need computational power, you need time, and now you need to figure out where should this computational power reside. So for that, we call this as a multiverse. Inspired by some of the recent Marvel movies that are coming out these days. So there is not just one twin, but there is a family of twins. Those twins reside at different locations at the edge, closer or farther away, that depending upon the network architecture design. And each time you create this one instance of the twin, it resides in the multiverse. So you can have a twin with high fidelity or a low fidelity, and you invoke the twin based on how much time do you have to make the decision, and at what resolution do you need that decision. So I won't go into the details, but we have been looking at this overall framework that marries this computational constraint with the benefit that you get from a good emulation of the system. So just to move a little bit forward, I want to give you a sense of what this digital world looks like. So on the right-hand side, you see the digital world created using Blender and Blenser for camera and LiDAR. And on the right-hand side, on your left-hand side, you see the real world captures from the car. Let me see if I can. Oops. how? No. Yeah, Yancy, how did you do the trick? I have nothing here though. Just wanted to play the video. Is that? Oh, there. Okay, so thank you, whoever is the magic one who did that. Thank you. So here is what you see. The car is moving, right? The car is moving, and and you will soon see a vehicle appearing. The car is trying to establish a connection with a roadside unit, which is just behind the vehicle, and to train such a scenario, we need to capture camera LiDAR images and the actual beam that was chosen at each point in time. So on your right-hand side, you see this entire scenario emulated in a system that we have created with wireless insight for ray tracing, with Blender and Blender, which are more open source packages, and combining together to accurately reflect what's happening in the real world. Just to give you a sense whether this works and how does this overall perform, here is the entire pipeline. We have the autonomous vehicle. We use it to collect actual ground truth data. We emulate this virtual environment. This ground truth data is used to calibrate as well as to shape this virtual environment. And we have other metrics where we say that this virtual environment is closely resembling the real world, right? We do some sorts of calibration measures to make sure that is actually established. Now, once that is established, we have a two-stage process. You can update the virtual world as new information comes up. For example, a big truck lined up in front, and that's a permanent obstacle. So that new information can be embedded inside the virtual world. At the same time, models learned in the virtual world are continuously shipped back into the real world for actuation decisions in real time. So you don't need the virtual world to be in the loop all the time. You can learn models offline, you can train them, and you can update your real world for continuous actions. So here is an example where you see the benefit of this entire virtual world and real world interaction. So what you see here are three instances of twins at different levels of fidelity. So the first one here is simply doing an omnidirectional transmissions. There is no special consideration of building structures and the kind of material for which it is reflecting from. The next one is going a step further, but is only assuming a single multipath, or rather a single ray or a single multipath effect. This one is looking at three possible multipaths. So it's sort of a richer environment, and thereby giving you a more complex reflection pattern, takes more time to compute. So as you look at these twins 1, 2, and 3, and you start to see their performance, you see this twin 3 is actually doing much better. And this plot tells you that how accurately am I predicting the top 10% of the beams that were chosen in the real world based on what I am with models trained entirely in the virtual world. So the more the fidelity of this emulation, the better you're going to do. And as you can see, for both line of sight and non-line of sight, we're actually doing better. Now, this is an open area. There are lots of exciting problems. The problems actually arise and very eloquently put forth in previous talks is to manage the computational constraints with the wireless constraints and with the expected output and benefit constraints. Right? So the good thing here is that we need to revise our vision that wireless or optimizing wireless should only be based on wireless inputs, or rather RF inputs. Not so. We should now start to think about how to harness that incredible amount of information that exists all around to affect wireless decisions. And that's the vision that I wanted to say. And just I'll leave you with that last picture. If Sir Magic Wand could please press this one once again and make this happen. So I just want to show you that here is the actual vehicle that is coming down. The roadside unit is what you see here on the side, and that's where it wants to establish a connection with. It is trying to find out places to bounce off the signal. Here is what the green part here shows where the digital twin predicted the correct beam with respect to what the real world did actually and where it failed. And you can see broadly, if trained well on good data, we are doing fairly well in terms of predicting what the real world does. So with that, I'll stop here and pass it on to the next.
Thank you very much, Kaushik. So we're going to take a very short break, 5 to 10 minutes, if you want to grab a coffee or a bottle of water, and then we'll continue with the presentations at 11:15. There's going to be 5 or 6 more presentations, and again, short, as similar to the first session. So please feel free to stretch a little bit and be back in the room in 5 minutes. All right, welcome back, everyone. We have the second session of faculty and researcher presentations. We have 6 more presentations between now and lunch. All exciting talks. As similar to the first session, we're going to keep it short but informative. Our first speaker is Dr. Michele Palesa. He's going to talk about rethinking the cellular architecture with Open RAN towards 6G.
Thanks, Pedram. Thanks, everyone, for being here. So I'm Michele Palesa. I'm a research scientist here at WIoT, and I'll present some thoughts on what we think comes next in terms of architectural developments for cellular networks, right? So 5G has been deployed. We have it in our phones today. And we're started thinking at what comes next, whether you want to call it NextG, whether you want to call it Future G, 6G, and so on. So in this short talk, I'll try to look at 6G system from an angle that is not much discussed from what I've seen in papers or in talks about 6G, which is the architectural perspective, which I think is a key to a successful deployment and upgrade of future cellular systems. And to understand why is this, we should take a step back and look at what is wrong with 5G. Some direction have already been mentioned, for example, by Ken. There were many promises. Some of them were under-delivered. So, for example, millimeter waves are not completely there. Okay, we have the theory, we have beam management algorithms like Kaushik was presenting, but deployments are still lagging. URLC is still behind, same for V2V and so on. And in general, there's a gap between standardization, which is now almost at release 17 of 3GPP, and deployments, which are still back in basically release 15. And this has a couple of reasons. There's for sure business and economic reasons, right? Millimeter waves are a hard proposition for operators because it's costly to deploy ultra-dense networks. But at the same time, there are technical reasons. And we as researchers can work to address part of these technical reasons. So in addition to this, rather than asking ourselves what's wrong with 5G, we can start and think about what's wrong with cellular in general. So cellular networks, as they are designed today, come with limited options for deployment. There's monolithic hardware. They are hard to update, hard to improve, hard to optimize. They are not flexible. They need to use licensed spectrum most of the time. You can control only what vendors expose. And this leads to a gap between some nice algorithmic optimization that you can do and that we study, and what you can actually do in practice. And the third point is that there is mostly a focus on broadband. So there is limited support for other kinds of traffic, of services. There is limited customizability of the networks, and the business case is mostly for broadband. So from these points, I think there's really a gap between principle and implementations, especially when it comes to the control plane. And this is why I think that we are in the right moment to start rethinking the cellular architecture as we head into the 6G standardization. And specifically, rethink the cellular architecture along these lines. So go beyond the license spectrum and go toward more agile system with spectrum and infrastructure sharing. And I'll talk a little bit about spectrum and infrastructure sharing and a nice system level implementation that we did of spectrum sharing systems. Toward more open and heterogeneous deployments, native orchestration for AI and ML, so practical ways to embed all the interesting AI and ML machinery that we've seen this morning in large-scale networks, closed-loop control, and finally, softwareization driven by cloud-native principle, which also includes security. Right? So these are some principles, and we see the Oran architecture that Tommaso briefly mentioned in the opening this morning as a way to bring this principle into a practical deployment. So this is a high-level diagram of the Oran architecture. I won't go into details, but I'll just mention that there are some key novelties. So open and standardized interfaces, the disaggregation of the RAN into multiple components, software and automation. But what we think is the most interesting novelty is the introduction of these RAN intelligent controllers, or RICs, at the edge and in the cloud that can basically drive and influence the behavior of the RAN itself. So the RAN intelligent controllers enable intelligent control loops that span different components of the network, have different timescales, and allow external applications to efficiently control the behavior of the RAN, control and optimize the behavior of the RAN at many different levels. So we've been doing a lot of research on this. Again, I won't go into details. I'm just trying to give a high-level overview. And based on what we've seen on the research that we've done so far, we think that there are still some key challenges toward the development of intelligent Open RAN, where one of them comes from the intelligent bit, so the need for dataset, platforms, development and testing of Open RAN solutions. The second one is use cases with AI that actually can work well in a variety of different scenarios and generalize well. And the third one refers to what I was mentioning earlier, so the possibility of being more agile in terms of how we use the spectrum, how we use the infrastructure, and where we deploy the AI. So we've been working to address these challenges. Among the different things that we've been doing, there's Open RAN Gym, which is a framework that tries to address the first challenge. So how can we get data sets and how can we test Open RAN systems? And the idea of Open RAN Gym is to have an end-to-end environment where we provide base stations, we provide the near real-time RIC platform, the no-real-time RIC is coming, and we provide basically a stub for intelligent applications that you can run on top of this infrastructure, where anybody can come in and add a piece of custom logic, of custom intelligence that can then be tested automatically on this infrastructure. We also worked on some intelligent ORAN use cases with PhD students and researchers here at WIoT, but also with industry collaborators. So for example, we've been working a lot of network slicing and scheduling, deciding how many resources to provide to different kind of classes of traffic. We've been working on traffic steering, so how can you efficiently balance the load and move users across the network so that each individual user gets the best QoS available. We've been working on spectrum sharing, and I'll talk a little bit more about this in a moment. and energy efficiency. So how can you dynamically scale your resources to use the minimum amount of compute when needed and avoid that new Open RAN system becomes detrimental toward the energy efficiency of the system. So as I mentioned in the last couple of minutes, I'll briefly talk about the spectrum and infrastructure sharing framework that we built over the last year, but we call Neutron because it's a neutral host solution. So a solution where you have some shared infrastructure, spectrum, and compute that is used to deploy different network functions from the core to the RAN to edge services, the RICs, AI, and ML, and so on, for different kind of tenants. And specifically, this is a neutral host enabled by Open RAN. So we have a set of orchestration, automation, and intelligent function allocation services that leverage Open RAN components to match tenant requests with the resources that are available. So this is a very high-level overview of the Neutron framework, which includes basically no real-time RIC or SMO, the edge data centers where you actually deploy your network, and cell sites where you have radios and spectrum. And the key component of Neutron is its optimization engine, RAP. RAP is an application that runs in timescales higher than 1 second. And so this allows to orchestrate the whole end-to-end network. It basically maximizes the resource allocation in terms of spectrum, compute, and AI ML capabilities. It satisfies, tries to satisfy at least the requests from the operators and the tenants. It avoids conflicts between the different tenants of the neutral host framework, and it also avoids interference. And it does this by accepting set of requests which are then parsed by an optimization engine that solves a binary quadratically constrained quadratic problem and return basically an allocation, an optimal allocation. So this is nice. It's an interesting optimization problem. The interesting thing is that we also implemented it in practice on a real cluster that runs a version of Kubernetes that is called OpenShift that we can automatically control based on the output of the optimization problem. We deployed this on the testbed that is 4th floor upstairs, Arena, the testbed that Tommaso was mentioning in the introduction, where we kind of deployed a solution with 4 cell sites, 3 different tenants that were competing for spectrum and infrastructure resources, and the Neutron framework basically solving the sharing problem and automatically deploying the whole network. And so what we've seen is that we're able to deploy a network in basically less than 10 seconds. This is the time that it takes to deploy a base station, a core network, and the XApps. And the second thing that we've seen is that sharing the infrastructure and the spectrum leads to improved performance with respect to the no sharing option. But at the same time, if you share and use only 1/3 of the spectrum, just by sharing and optimizing the allocation of the resources when you need them and where you need them, you can still improve the overall RAN performance. So this is all. Thanks, and I'll be available for questions at any time during the break.
Thank you, Michele. All right, on this next presentation, I'm going to talk about wireless digital twins and bridging the real-world experimentations to wireless network emulators. If they put up my slides. I think I have one. It's working. There we go. All right. Today we have been talking about different testbeds that we have at the Institute. And of course, at this point, I believe everybody is quite familiar with the largest wireless network emulator called Coliseum that is one of the facilities that is hosted at Northeastern University and the Institute. Network emulators, of course, everybody knows that they have a lot of flexibility in terms of being able to do repeatable experiments on them, and also they have a lot lower costs rather than doing real-world experimentations. So this is a unique capability that enables researchers to work on wireless assisted platforms and in particular emulation systems. But one of the questions that everybody started to ask us when we opened Coliseum to the public was, okay, so what is the fidelity of this emulation system? Are you actually creating a reliable replica of what is happening in the real world so that we can rely on that and then do the research on top of that? And during the past year or so, the researchers at the Institute, we have been putting together a set of tools to streamline the process of creating virtually any type of physical wireless environment. We create the digital twin version of that, and then we'll implement it on Coliseum so that researchers can reliably work on that. There are different components to that, thousands of lines of code that has been written by the researchers at the Institute. All of them are available for researchers to use. This is open source. I'm going to just briefly talk about some of these components, and of course later on in the poster session, if you have more detailed questions, we'll be happy to answer some of those. The block diagram that you see down here is essentially one of the example and use cases that we have been doing. Tommaso, Michele, and other people have been talking about Arena, which is one of our indoor real-world testbed platforms here at the ISEC 4th floor. In one of the practices, we have actually created a digital twin version of that, and we implemented it on Coliseum. The block diagram that you see here is actually summarizing that work, which I'm going to go through some of the details. Coliseum, we have talked about this again extensively. I'm not going to spend too much time on this slide, but just to show you two different components that enables real digital twins. One of them is on the RF environment, making sure that the wireless environment and the radio propagation and everything at the physical layer is actually a reliable and high fidelity representation of the physical world. And on top of that, of course, there's this concept of openness, programmability, open 5G, open 6G, and the notion of open RAN that all the governments around the globe are pushing towards that paradigm. And it's important to be able to grab the latest version of the code that's up there and being developed by developers all around the world, and then being able to adapt to that quickly and in an automated fashion. So that's the other part and component of this digital twinning tool set that we have put together for Coliseum. Real quick on the first part, the physical layer, it's obvious that any of these network emulators, they do have their own limitations. Coliseum in particular works based on FIR filter taps. This is a list of the restrictions that we have there. I'm not going to go through the details, but in general, you have a CIR, but what Coliseum can do for you is only representing 4 of those taps with a resolution which is 10 nanoseconds, and all the others should be 0. So you are already losing a little bit of accuracy there. So it's important to have an algorithm that optimizes the way that you are going from a continuous CIR to a sparse filter. This is the work that we call CAST. What it does, it has 2 components. One of them is creating those scenarios. That I have a slide on that that's coming up next. That's creating scenarios, and then the loop back there is sounding that scenario, and that's another part that we have put together. Again, open source can be used for everybody. The creation part is this slide, so you can start by identifying a location anywhere on the world. With open source maps, you can obtain that 3D model. It could be indoor or outdoor environment, and then you use your tools. It could be ray tracer, for example. Wireless Income is one of them that we have been using. You can use MATLAB ray trace function, or those 3 first blocks can be completely replaced by a stochastical model of your choice. Then after that, you set the nodes, the trajectory, the movements, the mobility between the nodes. You sample the channel, you parse the output, you approximate the channel, you make sure that your network emulator understands and is capable of playing that channel for you, and then you install the Coliseum. So this is the first component of the CAS that is creating those scenarios. And then, of course, the second part is doing the channel sounding. Again, I'm not going to go through the whole process here, but we use the best practice in channel sounding. This is nothing new, but the fact that having it being enabled on a network emulator based on software-defined radios is the unique part and the new contribution that we have done. This is a block diagram just explaining how this is done. Again, normal process, we have a code sequence, you send it through the MCAM, that's the massive channel emulator of Coliseum. In the massive channel emulator, that's essentially playing those taps for you. Those are the FIR tap filters that we have created based on ray tracing model, for example. And then you correlate that with what you receive on the receiver side, and then validate that with what you actually had at the very beginning. So this is a validation process or sounding process, making sure that whatever you're feeding your network emulator, it is actually acting the way that you're expecting that to act for you. Of course, everything is started from the lab with a simple testbed and software-defined radio. And we continue to create more and more of these examples. We already have a few that are open access and already up there. I'm going to show you a couple of examples. One of them is Arena. The other one is the collaboration that we are doing with Viavi, and this is happening this week. We are having a real-world measurement campaign, doing some sounding, creating signals in the real world, creating the digital twin version on Coliseum, and then we'll do the evaluation later. We have done this practice with many of our partners. The list is long. I'm not going to go over that. Some of the results, one of the very first interesting results that we were interested in was, so okay, what happens if I have like a 0 dB path loss on that channel emulator, and I have transmitters and receivers? So how closely are these 128 radios that I have on this huge wireless network emulator, how closely are they acting compared to each other? And that's a calibration phase that is also important for us to calibrate them, making sure that all those are similar to each other. The matrix that you see on the other side is showing you the path loss in a 0 dB path loss scenario. Of course, the result is not 0 dB. That's around 58 dB, and that's the loss that is coming from all the hardware that you have in the loop, including the attenuators, the cables, connectors, and whatnot. But it has to be consistent, and as of right now, this is one of the latest results that we have run on 25 nodes of Coliseum. There is a standard deviation of 1.2 dB difference between these two radios, and of course we have a calibration process that we can calibrate that and making sure that we make that as close as possible to each other for all the radios that we have. The other example is actually a 4-tap real scenario, a multi-path scenario. What you see, the blue line is what is actually happening at Coliseum after creating that scenario and installing in Coliseum. And then the red dots, the sparse 4 taps, is what we fed Coliseum with that model. And through that sounding process, we observed the blue curve. And this is a comparison between all those 4 taps, which is pretty much distinguishable. And that shows you a high fidelity network emulator system. And again, everyone who comes to Coliseum and wants to create a new scenario, we have this tool all set up for them. They can go through the sounding process and making sure that actually representing what they asked the emulator to do that for them. A couple of examples real quick on some of the projects that we have been doing. This is a project that was supported by Department of Transportation on vehicular communications. What you see down there is an actual real world scenario for vehicular communications, V2X. In particular, I have an RSU, roadside unit, and a couple of OBUs that are mounted on those 2 vehicles that are moving. That's close to the Tampa Highway Administration in Tampa, Florida, and that's an actual real-world testbed campaign that they have put together a few years ago. We've got some of the data from them, created that scenario on Coliseum. The graph that you see on top is actually the result of sounding that scenario on Coliseum and then comparing that to what happened in the real world, which is a perfect match. We call it the U shape and a V shape. The U shape is showing you the path loss. The V shape is actually telling you that there's a constant speed between those OBUs compared to the RSU, which is in the stationary node. And these are the other 2 curves, like the 2D cut of that 3D curve that you saw. Another example is the replicate of Arena, an indoor wireless testbed with 64 antennas here in ISEC 4th floor. Many of you, I'm sure that you have seen that. If you have not, we'll be more than happy to give you a little tour later tonight. So we have done that practice. We took that environment, indoor environment. We created a 3D model of that. We ran that in a ray tracing software. Based on that, we created the channel models. We put that on Coliseum, and then we went through that validation phase and sounding and making sure, optimizing everything and making sure that's actually a digital twin version of the real world. Some of the results, of course, there's a physical layer, but as I said earlier in this talk, we are interested in the higher layer parameters and making sure that actually what is happening on the higher layer of the protocol stack is also representing what's happening in the real world. Two examples that you see here on top, Arena and Coliseum. That's the Open RAN protocol stack that we ran on Arena and also on Coliseum. The results are pretty comparable. And then what you see at the bottom are two jamming scenarios with a narrowband and a wideband jamming signal, again in real world and in the digital twin version. Two different colors showing you SINR and throughput comparison between what is happening when I turn on the jamming signal. You can see the spectrogram down here. Whenever I have that jamming signal, the service will be degraded with the narrowband and also the wideband, and then the comparison between Coliseum and Arena, which is a perfect match. Lastly, I only have one or two more slides. That's on the protocol stack tuning. Again, as Michele was talking about, some of the components of Open RAN, and not just the protocol itself, which is being developed by developers all around the globe, but also the additional components like the Open RAN gym and the RAN intelligent controllers. Those are also being developed by people. So we have put together a tool chain, a CI/CD platform for continuous integration with what is being developed by the software developers. Again, this is publicly available and accessible to the users. I'm not going to go through the details, but what happens is, a set of tools and software platforms, all online, cloud-based, will take care of monitoring the repositories that contain the Open RAN newest versions of protocol stack, as well as other components, for example, the RAN intelligent control. So it will monitor those repositories as soon as there is a change and there's a new version. It will go ahead and fetch that new version. It will create a Linux container or a Docker image for you based on the platform that you're using it, and it will implement that on that platform, in this example on Coliseum or Arena for you, so that you are connected to the latest version of the code up there. So that's what we call the protocol tuning part, and of course the previous part was the RF tuning part. The work has been funded by multiple agencies, including NSF, Department of Transportation, and recently OUSD under the Open NextG work. And of course, this has been used extensively with many of our industry partners. Again, I think Dell, Qualcomm, Viavi, Keysight, many of them, and the list is long. I'm not going to go through the list, but we have done this practice to creating those models, whether it be indoor or outdoor, so that it will enable the wireless research on wireless network emulators. With that, I'm going to conclude this talk, and we'll be more than happy to take questions later on in the afternoon. Thank you. So our next speaker is Dr. Josep Jornet. He will be talking about terahertz communications from the near field to satellite networks.
Thank you very much, Pedram. Let's see if we get those slides up. Or not. I mean, I can entertain for as long as you want. I mean, that's not really a problem. Yeah, no, maybe singing is not the thing, but. Okay, there we go. So let's continue. Let's don't break the flow, and let's jump into terahertz communications. We'll start in the near field. We'll end up with satellite networks. You see where I'm going. So first of all, I believe that at this point, everyone in this room knows what to expect out of the terahertz band. We know that we can get very high-speed connectivity. Our goal is to get to terabit per second networks, and for everyone, while trying to remain secure, intrinsically secure thanks to the physics. We understand that at terahertz frequencies we can do sensing that can give us, if we need it, submillimetric resolution, but also spectroscopy, so the ability to classify elements in our surroundings just from their frequency response. And this is something unique to terahertz frequencies thanks to the terahertz photon energy. And we know we can do this in the macro scale, meaning in the type of applications that we have been hearing a lot today, right? For example, indoor smart connected spaces where, sure, transmitters, receivers, reflecting surfaces, and everything. But we also talk about the applications of terahertz at the nanoscale. For example, when we're dealing with implanted or even embedded in the body networks in which we take advantage not just of the communications, but of the sensing abilities and the spectroscopy of the terahertz band. Now, along this big thing, we've been doing many types of contributions, right? As Tommaso mentioned in the morning, on the one hand, we work on materials, devices, and we build testbeds. On the one hand, we have our own ideas of how we think we should make a terahertz radio, ideas that go beyond electronics, go beyond photonics. We talk about plasmonics, and we generate intellectual property on that, and you will see a poster about that today. We talk about not just the analog part of your radio, but your digital part. And I think it's clear from today's presentations already that digital signal processing, handling a lot of information is not simple, yet alone when you're trying to do that at terabit per second. So you're also going to see a poster on real-time ultra-broadband digital signal processing. We've done channel modeling. We are not a channel modeling group, but we understand that if we have to build a network, we need to understand what happens to our signals. And we have done the type of channel modeling that combines physics with data. And we have done that in the good things that Boster can give us, which is plenty of rain, plenty of snow. So we do that type of channel modeling too. Beyond that, of course, at the core of our group, we are a physical layer group, so we work on different types of modulations. You'll see a poster about that. MIMO, you'll see another poster about that. Intelligent surfaces, you'll see a demo about that. And joint communications and sensing that I'll mention a little bit. Beyond that, we build networks that are ultra-directional, networks that are ultra-broadband. And of course, we also want to think that we want to change the way in which we think of networks, because if anything we know at this moment is that the terahertz channel can be either really good or really bad. And maybe we don't just need to give all the problems to the physical layer people. Maybe we need to solve them some at the network layer. Beyond that, as Tommaso mentioned also in the introduction, we don't just stop with papers or patents, actually. We try to make an impact that it's global. That's why, for example, we're part of the ITU. Or that's why, for example, we submit recommendations or answer the request for information from FCC. We're working with exciting topics like coexistence between active and passive users, but also coexistence with people. And you know what? You're going to have another poster in which maybe you go check that posters first. We'll talk about the safety of terahertz radiation. Then you go and you decide how close you're going to get to our testbed. Okay? We also, make contributions to standardization. And for example, some of the physical layer solutions that we develop are now in the first amendment of the 802.15 3D standard for terahertz. Now, this is like, you say, okay, and how have you done this? Well, we have done this because we've been working on terahertz for the last 14 years. At the time that people thought that was science fiction, we were doing that. And through the years, we have been building the story. And by we, I really mean we as an institute, right? So we have worked with Tommaso, with Francesco, with Kaushik, with Dimitrios, with Milica. I mean, anyone that you can think of is involved in some way. Hope to get something with Ken too, because I've talked many things. There is no error control here. So we need that, for example. Or not, maybe we don't need it. We just don't need error control anymore. Having said that, some of the things that have been exciting during this last year, and hopefully you saw the news, is that one of the things that we did was to demonstrate the longest link at 225 gigahertz carrying real-time data out of a few gigabits per second. Where did we do that? We did this in collaboration with JPL and AFRL. We did this in Rome, New York, in one of their facilities. It's a public facility. I mean, it's a disclosable facility. And yes, it was a link with line of sight with a transmitter on one hill, the receiver on the other hill, 2 kilometers apart. Now, how did we do that? Some people will say, oh, terahertz communications today make sense just because you have better devices. And of course, I want to give credit to my colleagues who are actually building new devices. But an improvement in a technology doesn't come just because you do one thing. It comes from many things. And in this case, it's the co-design of integration of devices with the actual signal processing we do with them. And we can do that better because we understand the channel. So you see how everything builds up. So that's the key idea. In this case, we did use world record high-powered transceivers from NASA JPL, with whom the Institute has a Space Act agreement for exchange of not just technology, but also people. Some of our students have been at JPL in the last couple of summers, so that's good. But these architectures that they gave us actually were a radar system. They didn't have a mixer. There was no way for me to inject information there. So we had to be creative and see where we can put either the information or try to get a mixer somewhere else. So those are the type of things that we are doing. And for example, this application, we presented in the context of bridging the rural digital divide. I can give you a technology that can give you fiber-like connectivity over long distances without having to deploy fiber. And this afternoon, you will hear a little bit more about this in the context of entrepreneurship in the Institute. So I stop here. I don't want to take the show from Hussam. Now, those are things that we already published. So what is keeping us busy these days? Let's start with the following. One of the ways we overcome the very high losses at terahertz frequencies and the not that much power is, well, using higher gain directional antennas, or in other words, using large antennas, whether they are at the transmitter, at the receiver, or along the walls in the form of intelligent reflecting surfaces. Now what happened? Well, if you make your antennas physically large in terms of wavelength, what's going to happen is that the thing that we call the far field, it's going to be very far. For example, the far field of a radiating structure goes with 2d to the power of 2 divided by lambda, where this is the largest antenna dimension. If you have an antenna which is 20 centimeters, whether the antenna, the array, or a reflector array, at 120 gigahertz, your far field, the typical assumptions that we do in all our communication design, starts at 32 meters. If you go to 300 gigahertz, it starts at 80 meters. If you decide, no, let me go at 1 terahertz, don't ask me how. Well, you will see how, because we actually show you one of our terahertz front ends at 1 terahertz from Virginia diodes, who are also here. Our far field doesn't start at 267 meters. And you will say, sure, so the far field is far. What do I get out of that? Well, the problem is that all the technologies that we have been using, all the traditional beamforming, assumes that you are in the far field. And the reality is that in many of our applications, we're going to be within the near field. Now, what do we do in the near field? Is it a problem or is it an opportunity? The community in the last 2 years have discovered this, and they are presenting it as a problem that we have to solve. I'm going to tell you that that's not a problem. That's actually one of the best things that could happen to the field. Why? Well, when you are in the near field, there are new things that you can do with your signals besides just deciding in which direction they go. You can start shaping the way they look at you when they come to you. Forget about plane wave, forget about spherical wave, which is what some people relate near field to. Let's talk about exciting things. For example, the community so far has been focused, and by the community I really mean the wireless physical layer community, has been mostly focused on saying, look, we are in the near field, we don't do beamforming, we do beam focusing, like if we had a lens. What is beam focusing is to send your signals in a way or manipulate the phases of your signal emulating a lens. And sure, then you can focus at a point. The problem is that you step to the right, you step to the left, you move your hand, you are out of focus. So that's not really ideal, but that's okay. Plenty of papers are coming out of that. We are not going to prevent the community from doing that. But what are we doing? Well, if we are in the near field, there are more interesting things we can do. One of them, for example, instead of just trying to focus at a point or trying to launch a plane wave, we can generate a field distribution that looks like a Bessel function. You will say, why would I do that? Well, first of all, because it's a solution to the wave equation, so that's great. But more importantly, is because Bessel functions focus along a line. So if you want to do beamforming, which is you want to send your signal in a given direction where your user is, if you do your typical beamforming, you're not going to really form in the near field, so forget about it. But if you really want to beamform in the near field, then you, at the very least, can use Bessel beams. I'll give you more hints in the next slide of what's better than that. Another thing that we can do is we can also use, for example, 80 beams. 80 beams are beams that exist in the near field, and that what's interesting is that you can launch them along a line that bends. So you can send a signal without any interaction in the medium, just from how you program it at the origin, and have it bend right, left, up, or down. It's like throwing a ball with a curve. Okay? It's exactly the same. And how can we do that? Well, we can do that just by manipulating the phase and the intensity of the signal as we launch it. What's the additional bonuses that you get out of this? Well, you can probably start thinking. In here on the left, we're actually showing that one of the big problems of millimeter wave, and of course by extension of terahertz, is blockage. You know what? There are many interesting properties out of these different waveforms that I mentioned. If you're doing beamforming and you put an obstacle, in this figure you have a transmitter on the left, a receiver on the right for each possible type of beam that we can send. If you try to do beamforming and you have an obstacle, you're going to create a shadow, so nothing. If you're doing beam focusing, you might be able to focus after the obstacle, so actually that's quite good. If you're doing bezel beams, look, even if you block the core of your beam, after a few wavelengths, your beam has regenerated. Why? That's a property of bezel functions. They are self-healing. As long as we don't fully block it, the signal reappears with a strength. So maybe to overcome blockage, we don't need just to find other path. We just need to find signals that self-heal. And this is not magic. This is actually physics, so we're good. Now, what is 80 beams? Same thing. You try to communicate around a corner. Usually you say, I'll put a mirror there. You can put a mirror, or you can launch your signal to bend around the corner. These are all real things. And I'll give you an example. We'll show you some ways to implement bezel beams today in the afternoon in one of the setups in the demos. I'm showing you on the top figure your receive constellation when you send a typical Gaussian beam. Gaussian beam means what you do when you do beamforming. A Gaussian beam in the presence of an obstacle, the same beam, but now engineered as a bezel beam in the presence of an obstacle. I don't recover my constellation up there, I recover my constellation down here. I can regenerate signals going through obstacles at terahertz frequencies just by playing with how I launch those signals. That's great. That's exciting. Now, what else can I do with these wavefronts? Well, I can do other things that probably you have already heard about. I can take my signal, and instead of sending it to you with a given phase, I can send it to you with any phase I want, a plane wave, a spherical wave, a bezel beam, but I can also send it to you twisting over itself. We call that orbital angular momentum. And that's one of the properties that, look, if you're already comfortable doing all these fancy things to your signals, well, why don't you bring that in? That's a way people at some point said, oh, this orbital angular momentum looks like MIMO. It is MIMO. It's a way to generate orthogonal channels, because you know different spirals turning at different speed are giving you orthogonal channels. That's what you want if you want to increase in capacity. I'm pointing to Francesco. Yes, we need MIMO, as he said. You know, you're not going to have 60 gigahertz of bandwidth. So let's use the spectrum more efficiently. That's another way to get intrinsically MIMO modes, orthogonal MIMO modes. Now, how do we do this? Well, our colleagues in optics, we did not just discover bezel beams. This is something that at optics, people have been doing for a while in the context of sensing. And usually they use lenses for that. For bezel beams, axicons. For orbital angular momentum, spiral phase plates. Now, how can we do that? Well, we don't need to go to having an actual lens, which we'll show you today, by the way. We can also engineer those with antenna arrays. Antenna arrays that ideally should have less than half a wavelength spacing. So yes, metasurfaces make sense. And I think that it's just great. Actually, you're going to see some of this today in the afternoon in the demos. And the key idea here is the following. We have been investing a lot into going to higher frequencies. We have been investing a lot into reflecting surfaces. For what? Just to direct the signal one way or another? No, actually, we can start playing with all these very exciting things. And as I'm saying here, I think that everything starts to make sense. For years, when people ask me, Giuseppe, why do you terahertz? It's only for the bandwidth, and sure, then you are more directional. Actually, no. Suddenly, everything makes sense. It's more bandwidth, and yes, you are directional, but just because of how you deal with your signals, you're opening the door to the beautiful land of wavefront engineering. I'm being able to send self-healing signals, self-curving signals, twisted signals, and we can do that today. We can do that today in the lab. We can bring this very deep tightening with physics into our systems, which also means that there are many research questions that we need to answer, like how does the channel model look like if I'm not in the far field, but I'm in the near field? Do we need to tell Rappaport to go and redo all the measurements? Well, he doesn't know yet, but actually half of his measurements were in the near field. Don't tell me how you mapped that to a far field model. Don't ask me. I don't know how people do it. Now, how does interference look like using different wavefronts? How do you do beam steering of a bezel beam? There are many questions. It's a very fertile line for PhD topics, and now my students are like, don't give our ideas away. I'm not doing that. It's also fertile land for IP, intellectual property, and we're getting that, right? So we'll talk in the afternoons, or in the afternoon ways of engaging on this. Now, I'm almost done. What's then the next frontier for terahertz communications? We're already doing this, right? So what is next? What can be exciting out of that pyramid? Well, this is the first time that we say this in public as an institute. Funny things, WIoT is going to be launching not just one, but 2 satellites We've been approved by NASA, not just approved, supported by NASA through the CubeSat Launch Initiative to deploy, first design, then test, then deploy, what's going to be the first satellite system in space with terahertz inter-satellite communication link technology. This was announced by NASA a few weeks ago. We haven't made much noise yet. We thought that this was a good opportunity, and we're going to hear more about this. This is happening. I'm not saying that I'm going to write a paper on how you could do inter-satellite terahertz communications. We already wrote that paper. Actually, it should be somewhere in the figure. But what I'm saying is that literally this institute in, let's say, I think that the time constraint was between 2024 and 2027, we're going to be launching those satellites. Actually, they are going to be launched from the International Space Station, 2 satellites that will be twins, and then they will, with a very minor kick, they will be split. And as they split, that depending on how we design this splitting system will be for longer or for less, we're going to be measuring channel performance. We're going to be trying different solutions. As a matter of fact, we're going to try to interfere with those satellites from the ground and tell people that that's very hard. And this is happening. So yes, that's next. You have another poster with more details about this mission today. So again, plenty of posters. And you thought I was done. Actually, when you thought that you have heard everything about terahertz, well, we have another poster. In collaboration with another member of our institute, Shufeng Zhang, and as well as Kaushik, we have been working on, does it make sense to adopt quantum communications? And you know me, I only know how to do terahertz. So does it make sense to talk about terahertz quantum communications? The answer, we have a poster for that. Thank you very much. If you find any of these faces, you can go and ask anything that I said here. They are the real heroes there. They are the ones that are doing the work. I'm just the marketing agent. Thank you.
Thank you very much, Dr. Jornet. Our next presentation is going to be about platforms for advanced wireless research, PAWR, and Coliseum. And Manu Hossain, the director of the Power Platforms, is going to present that for us.
Thanks, Pedram. Slide adjuster. Perfect. Good afternoon, folks. So as Pedram introduced me, Manu Hossain, or as I like to say, the guy between you and lunch. So here to talk about the Power Platforms. Just a quick show of hands if you've heard about this research initiative. It was kicked off by the Science Foundation in 2017. OK, awesome. Thank you. So that makes me have been doing my day job. Partly, I want to connect the theme that you've heard throughout the day so far and some of the research pillars that the Institute here has been focused on. Sort of zooming out 10,000 feet, this is sort of an initiative which was strategically taken on under the leadership of Tommaso, Kaushik, and Stefano, and then I was engaged to lead the program on the Northeastern WIoT side. But this was more strategic in terms of building a public-private partnership model, which has now sort of kind of melded into the ethos of the Institute, which is how do you build research partnerships, how do you maintain partnerships, what are the key attributes that industry is looking for, and how do you bridge the chasm between fundamental research, applied research, and then moving into IP, large-scale testing, prototyping, et cetera. And then to level set, we're going to connect that back to some of the test assets and test platforms we have here at the Institute, primarily Coliseum, and how that fits under the Power umbrella. Okay, so real quick, turn back clock, the year's 2017. This is an initiative that the National Science Foundation wants to kick off. It's, till date, one of their largest flagship test research platform projects, primarily focused on wireless comms. It was about $100 million total investment over a period of 5 years. And this was to build large-scale city testbeds to, again, as I said, bridge the chasm between fundamental research over into applied research, prototyping, and proof of concepts. And again, if you go back to 2017, mobile communications, 5G was still in its infancy, not necessarily deployed. Some of the component technologies were out there, but there was industry which was quite hungry, and so was academia, to do some testing, prototyping at scale. And this was a paradigm shift because traditionally NSF has funded MRIs, CRIs, which are small programs which have largely benefited some of the university faculty here as well as faculty broadly in the US. But this was an idea to coalesce that investment and put the dollars to use in a large-scale, city-scale environment, and then also bring industry on board. So Northeastern University, alongside US Ignite, which is our partner 501c3 in DC that manages more of the finance and industry relationships, we teamed up together supported by the NSF, formed the Power Project Office, and this was the key pillar that was setting the strategic vision on what the test platforms are going to do in conjunction with managing the industry partnerships as well as the needs on the federal ecosystem side. So the stakeholders that we have are researchers, which we represent the constituency for, the industry partners, as well as the communities where these test platforms have been set up. Just a quick pass through of some of the industry members. There is some overlap with the WIoT industry membership base as well. Some of those logos probably need some updating, but basically gives you a viewpoint that this exposed us, the members of the faculty, as well as our students, by being part of this program to the entire telecom value chain to really understand what the pain points were and then sort of really bring that back in to understand where the research focus should be. Okay, so real quick, what's our portfolio? What have we been up to for the past 5 years? Recently, at least the project office side was kind of re-upped for another 3 years. So we're going to be in existence up until 2026, and then we're going to figure out what the sustainability model is going to be. But this is what we have as part of a portfolio. So these are geographically diverse, technology diverse, but the main spirit here is to build these test platforms on pillars of programmability end-to-end, and this is again, similar to what we've seen in some of the test platforms that you've seen that are of smaller scale, but here within WIoT, both here as well as at the Innovation Campus. So starting from the left, the first two cohort we have is Powder Cosmos, so there is sort of a fine line as how we've evolved based on some of the industry needs. So Powder and Cosmos, respectively in Salt Lake City, Utah, and downtown New York near Columbia University, have been set up primarily to be programmable end-to-end. So think software-defined radios, programmable network switches, reconfigurable optical add-drop multiplexers, programmable RF front ends, compute all the way, both horizontally and vertically. And these are at scale. So the Powder Testbeds is about 2 square miles, different kind of form factors centered around the University of Utah campus and primarily focused on SDN, massive MIMO, that's technology supplied by Rice University in the form of the Argos test platform. And then software-defined radios, primarily DC to 6. This has now obviously evolved given the programmable nature. So these were, just think about the complexity involved here, because these platforms were envisioned back in 2017-18, and to stay relevant in 2023 and beyond, these are still being heavily utilized by the academic membership and industry because of that strategic vision we had in the early days to have flexibility, modularity, as well as the idea of being able to insert new technologies as they mature and develop. Cosmos, primarily, if you were to take two key takeaways, this is research focused primarily on millimeter wave, as well as on the optical domain, so PONs, passive optical networks, as well as ROADMs, so reconfigurable optical networks, where you can take the RF signals and basically transmit them over the physical layer in the form of light, so really, really fast. And all of this can be switched. It's set up as a star topology physically, but then you can actually program the signals to go in however you'd wish. So this is primarily very dense, about 0.9 square miles, but the idea being that you have dense software-defined millimeter wave capability for channel modeling, for comms, as well as for real-world applications. Then a year and a half later, we sort of shifted focus to be a little bit more closer to industry. As 5G and other technologies were developing and maturing, we moved on to test platforms that focused on the application domain. So we funded a test research platform at North Carolina State University called AirPow that focuses primarily on high mobility and unmanned aerial vehicles. So this is looking at building unmanned aerial vehicles, inserting comms into the third dimension. So now you're looking at X, Y domain, but also the Z domain. So very rich field, even very relevant today. Lots of research challenges, research problems, very complex, very complicated. But again, it's a test platform. It's an asset available to you as a student here. And all of this is completely underwritten by investment by the National Science Foundation. If you're an industry member, call to action here. If any of this piques your interest, please come find me. I'll be here for the rest of the day, and we can talk about how we can engage industry in there. Last but not the least, about a year and a half ago, the last platform that was selected and funded was to address the notion of the rural digital divide and to address technologies for rural broadband. So this was looking at the X-haul piece, so mid-band, front haul, mid-haul, front haul, and backhaul technologies. And the key innovation here is looking at free space optical communications that's being deployed there. How does this all tie back into Coliseum? That's sort of the main theme, and I'll really quickly go into there. I'm not going to go into details of Coliseum. Mostly things were covered by Pedram, and there are going to be some posters on how Coliseum is being utilized. But that's sort of the primary tie-in piece that connects all of those platforms and brings this back into the virtual domain. This I'm going to skip. So these are all the different topic areas. If any of these, again, pique your interest, happy to sort of send you pointers on how that research is being conducted. Huge list of publications, et cetera. A lot of that also coming from the Institute, but also from academics all over the country and the globe. So Coliseum, we've heard this earlier today. This is another key piece where we're seeing a lot of interest both in Power and Coliseum, and there's a strong overlap in terms of communities who are funding. So everything that you've seen in the talks, support that's coming from different kind of federal research labs, but also non-traditional sources that primarily have, we've had a hard time trying to finding common research problems that we could jointly address. So all the way from the DoD S&T community to the academic community, as well as industry partners that are well represented here. So again, skipping the Coliseum details in the interest of time, I think what I want to focus on or have a main key takeaway is for the Coliseum is the channel emulation system, right? So we heard Pedram sort of talk about the digital twin architecture, and he talked about sort of the filter taps that need to be programmed and the data sets that need to be produced. So the key common theme here with the power platforms is these are real world platforms, real world radios, real world locations, real channel and network models, and Coliseum is a hungry beast that basically needs to ingest the large amounts of data that's generated from the power platforms. And that's sort of what allows us to build the scenarios and the rich diversity of channel and network models that can then be leveraged by the academic community, by industry, to have rich fidelity on which some of the topic areas that you want to explore, whether it be Open RAN, whether it be spectrum sharing, can actually be documented. So scenarios, obviously, this is the Coliseum way, where we talked about the 4 non-zero filter taps. How do you program them? Some of the scenarios that you've probably seen, these are the ones that were developed here by researchers at WIoT and then contributed back. So team, both for Tommaso and Kaushik's team, sort of worked hard to build these, and these data sets are now also available beyond the use of Coliseum. And where we're seeing a large utility of this is in training AI/ML models, and I'm sure you're going to hear a lot more about the research that's being done there. Okay, so the punchline here, right? So what we've been doing, and this is again a concept that was conceptualized here under the auspices of WIoT, and then really has utility for power, but really generically for any test platform, given the common denominator that we focused on, which is a container. So the idea of the containers on Coliseum, which are the LXC containers, that's basically a self-contained utility of a programmable protocol stack that can be instantiated very quickly in Coliseum. But the idea is that you as a researcher individually can develop, whether it be Wi-Fi, 5G, LoRa, Bluetooth, any kind of a paradigm or even a networking protocol stack, and instantiate that on a Coliseum standard radio node. And then you have the ability to basically test this scenario at scale in the emulation environment, and then port this over to an indoor testbed arena in the case of WIoT, or this could be another homegrown lab infrastructure that you have. The idea here is that the portability of that container, given the underlying theme, and this could either be LXC or Kubernetes. Obviously, there is some glue code that needs to go in to make things work seamlessly, but this is something that has been proven, and there are research papers that have been published by the Institute on this. And then lastly, you sort of take these experiments and bring it out into the wild. The arrow that I don't show here is sort of this closed loop system where you can actually bring that fidelity research and testing back into the front, which is again testing it back on Coliseum, and all of this can be done in an autonomous way, all leveraging kind of some of the open source tools and pipelines that have been developed. Okay, so I'll wrap it up. Idea being, key takeaways here is Coliseum, which was sort of, we've sort of brought that under the Power umbrella as a Power affiliated testbed. It still is a standalone testbed, still a very proud asset for WIoT. And the idea is that some of the platforms that generate these large scale data sets are ingested into Coliseum, and sort of there's a contribution and a back and forth that allows us to have a very rich interaction between the real world environment and the virtual environment. And then the ease of container migration, which allows for repeatability across Coliseum and Power. We feel that this is going to be a paradigm for experimentation for sort of years to come, and credit goes to some of the researchers here. So with that, thank you for your time and attention here for the rest of the day. Let's break for lunch. Pedram?
Thanks, Manu, for the presentation. So we have 2 more talks before lunch. It's going to be brief. Our next presentation is going to be Dr. Dimitrios Kotsonikolas. He's going to be talking about gigabit per second speeds with 5G, and are we there yet? Okay.
Are we ready? Okay. Well, 2 more talks, right? So some more patience. Thanks. The title of the talk is Gigabit speeds with 5G. Are we there yet? So 2 talks ago, right, Josep talked about 6G, terahertz, terabits per second. We also saw a few other talks by colleagues talking about exciting new applications, ML-based, edge-assisted applications that require gigabit speeds. In this talk, I want to take a step back, and instead of thinking, what is going to happen in the future, I want to see what is happening today, what is the current state of the affairs with 5G, and what do we have to do to eventually implement, make that next generation of exciting applications a reality. So as we all know, 5G started rolling out in 2019, and we have witnessed a rapid deployment over the past 3-4 years by US major cellular operators. 5G promises ultra-high bandwidth, ultra-low latency, much better, at least compared to LTE. In the mid-band, you can already get hundreds of megabps of bandwidth. In the millimeter wave, you can get currently up to 3.5 gigabps. And these bandwidths have the potential to unlock many new applications that, again, some of my colleagues already talked about: Ultra HD 360-degree volumetric video streaming, AR, VR, XR, connected autonomous vehicles, digital twins, and so on. Now, all those applications, those 5G killer apps, as we call them, they are cloud or edge assisted. They need to process large volumes of data, and the processing tasks such as SLAM or object detection or frame rendering at high rates cannot be done on resource-constrained mobile devices. So we need powerful servers for that. So these applications exchange large data volumes with the cloud or the edge, either on the uplink direction, uploading camera frames or LiDAR point clouds, or in the downlink direction, downloading rendered frames. And at the same time, these applications have very stringent latency requirements. A few examples here. If you're doing a VR application, right, the motion to photon latency has to be below 15 ms to avoid dizziness. If you're running AR or VR applications and you want a fully immersive experience, many references talk about a minimum frame rate of 30 FPS for AR, even higher, 60 to 90 FPS for VR. And finally, in the case of autonomous vehicles, many references say that the end-to-end latency from the moment your LiDAR, for example, captures a scene to the moment you get the result of processing that scene, right, the identified objects, you need an end-to-end latency of 100 ms to have enough time to react and avoid obstacles. So 5G killer apps are both bandwidth and latency critical. Now, there are a few challenges in order to make those apps a reality. Even though 5G is here, right, it's been here for 4 years, it gives us gigabps speeds, but a few things to keep in mind. First, similar to all its predecessors, 5G is highly asymmetric. You get gigabps speeds, but only in the downlink direction. And many of these applications are actually uplink oriented. Second, higher frequencies means shorter range, right? So more horizontal handovers from one base station to the other, and potentially more coverage holes, which means more vertical handovers, degrading downgrading from 5G millimeter wave, for example, to a lower frequency 5G or to LTE. And finally, the ultimate question, mobility. Can we really maintain those high data rates under mobility, and in particular under extreme mobility, under driving? So this is actually the part, the focus of the rest of this talk. So we wanted to understand how 5G performs on the wheels. Okay, how 5G performs during driving. So how do you answer this question? Well, you get on the car, drive, and do measurements, right? So that's what we did. We got a car in LA, California. We equipped it with a bunch of smartphones running different applications, from simple applications measuring throughput or latency to applications running AR, 360-degree video streaming, mobile gaming, emulating a connected autonomous vehicle, LiDAR offloading, and so on, right? We also instrumented all those phones with XCAL devices that capture all the messages at the lower layers of the protocol stack exchanged between the base station and the phone. We deployed a bunch of cloud and edge servers in different parts of the country, and then we started driving. We drove 5,700 kilometers in 8 days from LA to Boston, measuring along the way, right? Measuring the networks of all the 3 major operators. We got about 400 gigabytes of data logs, and we are in the process of processing now these data logs, right? And we want to study coverage, handovers, which I will skip here in this talk, network performance, and application performance. So let's see just a few highlights of this data. So first of all, coverage today, 5G coverage, is actually disappointingly low, at least when it comes to driving in the highways, right? So here I'm breaking each band into smaller sub cases, right? I'm using 2 LTE bands, LTE and LTE advanced, and then for 5G, I'm talking about 5G low, 5G mid-band, and 5G millimeter wave. So you can see that only one operator actually has 60% of the total miles driven covered with 5G, at least some 5G technology. For the other 2 operators, the performance, the percentage of the miles that we drove where we were connected to any 5G was about 20% or less. And when it comes to fast 5G, right, mid-band or millimeter wave, the percentage is even lower. So if we go to performance, the upper graphs show performance CDFs of the 3 operators in 8 static scenarios, in 8 cities along this strip. Okay, and you can see that yes, 5G indeed can give gigabps speeds, right? More than 3 gigabps. But as I mentioned before, only in the downlink direction. In the uplink, you get at most 300 Mbps. And even in static scenarios, that's not always the case, right? The performance can vary a lot. So there's no guarantee that you will get gigabps speeds. Now, if you go to the driving performance, the lower row of graphs, you see again the performance currently is disappointing, right? And if I focus more on this, on the x-axis here, I just cut the x-axis, right, to see the CDFs clearly. We see that in the downlink, we got no more than 200 Mbps while driving, and maybe 80% of the time, the performance was no more than 50, 60 Mbps. In the uplink, 80% of the time, the performance was no more than 20 megabps. And if you look finally at the round-trip times, they can be great. They can be as low as 8, 9 milliseconds, but they can be as bad as 150 milliseconds. And remember here, right, for autonomous vehicle applications, you often need 100 milliseconds, which is not always possible, even when the car is parked. For an augmented reality app at 30 FPS, you need 33 milliseconds end-to-end latency, which is possible half of the time with one operator only in static conditions, and 20% of the time during driving. If you're talking about VR and you need 15 milliseconds end-to-end latency, well, forget it with the current state of the art, right? So performance per technology, here I'm just using one operator as an example. I'm not going to analyze all these graphs. One thing I want to finalize, you see solid lines, measurements with a cloud server, and dashed lines, measurements with an edge server. First of all, you can see that the edge can really help boost the performance for any technology. For example, in fact, you can see here that LTE with edge can be better than 5G mid-band with a cloud server, right? Second, when you come to the latency, you can see that combining millimeter wave and edge computing actually is really required in order to meet the demands of these new applications. This was the only case where we were able to get actually latency, end-to-end latency below 30 milliseconds. Okay, how much time do I have? Okay, I'm going to give an example of an application here. So an edge-assisted AR application that captures camera frames and offloads it to a server that performs object detection. Well, there is currently no such commercial app. Well, guess why? Because no network can support this kind of apps yet, right? So we implemented such an app that offloads frames at 30 FPS, performs optional compression, performs local tracking in case the result from the server doesn't come back in time. We used a high-end GPU, right? Now, the results here, the black dashed line at each graph show the best possible static performance that we got among all the tests that we ran in this trip. Now, you can see that the end-to-end latency, right, during driving, the red CDFs is much worse, right? Remember, we have a target here of 33 ms end-to-end latency, right? You're seeing that the end-to-end latency, in fact, can be up to 1 second or more during driving. This results, of course, in very low frames per second, right? Very low frame rate. Even in static, in the best static case, we were able to get at most 12 FPS. In driving conditions, we never got more than 5 FPS. And the last graph shows the MAP, the mean average precision. That's a metric used in computer vision, right? All you need to know, in case you haven't heard about this metric, the higher the better. So we can see again that during driving, the performance, the accuracy of object detection was much worse than the best static scenario. Okay, here I'm trying to see how having a fast 5G connection helps, right? So the x-axis shows the percentage of time for any given run where the phone was connected to mid-band or millimeter wave 5G. We see that fast 5G can help eliminate some very poor performance, but it doesn't really boost the performance compared to LTE, at least today, right? On the other hand, if you compare the dots where we were using a cloud server versus the crosses where we were using an edge server, you can easily see, right, that edge helps again a lot. Most of the cross marks here are gathered at the upper part of these figures. Finally, an interesting thing, the number of handovers doesn't seem to have an impact in the application. I can talk about why offline, right? Whether you have 5 handovers or 0 handovers, the performance is more or less the same. Again, what really makes a difference is the use of an edge or a cloud server. Okay, that's another example which I will not describe in detail. That's running an Ultra HD 360-degree video streaming application. We were able to play the video without any rebuffer only 20% of the time during this trip. In all the other cases, we encountered rebuffers, and in the median case, the rebuffer, well, half of the time, the rebuffering was more than 30%. So, to conclude, 5G current today offers what it promised, offers hundreds of megabps, up to 3 gigabps or more of data rates, but only in ideal scenarios, static line of sight, and only in the downlink direction. On the other hand, coverage and performance are disappointingly low still during driving, 4 years after the initial rollout. And 5G killer apps cannot be supported by today's cellular networks. So 3 takeaways, I think, here. First, high bandwidth alone is not enough. You need also to look at the latency. And when I'm talking about latency, I'm talking about the end-to-end latency, not just the run latency that will be improved by moving from 4G to 5G to 6G, right? You need to take care of the end-to-end latency. And that highlights the importance of edge computing. That's how you bring the end-to-end latency down, by deploying servers closer and closer to the base stations. Overall, I think that hardware advancements, both on the mobile device side and on the server side, and innovations across the full networking stack are needed in order to support this next generation of mobile apps, in addition to better physical layers, to faster data rates. So quickly, I'm going to finish with a few projects I'm currently working on. Some previous talks mentioned the ex-mili testbed. There is a poster in the afternoon presented by my student Imran, so I'm not listing it here again, but please go and see it. So we are currently working with Cisco on fine-grained throughput and latency prediction for next-generation mobile apps. We're also working with Cisco on application layer optimizations for mobile edge-assisted AR. And recently we started some work focusing more on the network side with AT&T. My student Moinak has a poster on multi-user AR in the afternoon. Go and take a look. Another piece of work is on understanding 5G operator policies. Of course, the operators know their policies, but the research community doesn't know them. So we try to uncover them by designing proper measurement methodologies without having access to the base station side. So my other student, Fug, will give an example of resource allocation policies in 5G millimeter wave networks in a poster in the afternoon. And finally, a recent work we started has nothing to do with performance. We're trying to do 5G millimeter wave localization. The idea here is to leverage the millimeter wave beams to do localization without GPS. Thanks, and I'm happy to answer any questions later today.
Thank you, Dimitrios. Our last but not least speaker is Professor Edmond Ye. He will be talking about networking for a new era of data, computation, and learning.
Is that working?
That's the point.
Okay.
If you want this is the clicker. Advancing the slides.
Okay. All right. Yeah. Great to be here. Thank you so much. What am I going to tell you in the next 10, 15 minutes that's going to hold your attention? We're going to talk about networking. Networking, I believe, really is going into a new era where I think traditionally networking is about who's talking to whom, right? Source, destination. That was the focus of networking ever since Alexander Graham Bell. It really now is more concerned with delivering data, managing computations, and learning. And that's what I'm going to focus on. So this is joint work with many people over the years, many of whom are sitting here. And so I think so. Dimitrios' talk set this up very well because he talked about edge computing, the importance of edge computing. We have many new applications, IoT, machine-to-machine, connected vehicles, et cetera, that what they want are things like low latency, locality, context awareness, privacy, interactivity, real-time control. And there's definitely been a movement toward edge and decentralization. Some years ago, The Economist had an article in which they talked about the cycles of decentralization and centralization. So we had mainframes, which were centralized. Then we had PCs, which were decentralized. Then we had cloud, which was centralized. And now we're going to the edge, which is decentralized. Okay, so this has been the latest iteration. There are new business models that are relevant to this conference. We want IT cloud services close to the edge, virtualized end-to-end services, and edge computing is certainly a fundamental part of 5G. Okay, so our lab really is focusing on networking for big data. I'll just list real fast some projects here. We have actually worked quite a bit. Is it possible to go back? Yeah. With companies, including Cisco and American Tower and Intel on a lot of these edge computing problems at the wireless edge. All right, so we have applications such as smart cities, connected cars, Industry 4.0, gaming, VR, AR. And what are these things looking for? So in edge computing, we're looking for IT service environment, cloud computing capability at the edge. It's a core technology of 5G, and of course, the G's afterwards, driven by these applications, which I mentioned. The point is to do computation and processing close to the mobile edge, so get low latency, high responsiveness, critical for mission-critical applications, interactivity, real-time control. And it's interesting to mention a lot of these computations are also data-intensive because the data that is being collected is also sitting at the edge. They need geographically distributed implementation. Location and context are very important. And in fact, a lot of these loads, these computations that have to be done, have to do with learning. All right. So there are many benefits, including real-time network, taking into account real-time network connected conditions, real-time network conditions. We want to exploit storage and computation resources close to the mobile edge to offload the burden on the front haul and the back haul, decreasing network costs. So therefore, caching becomes very important here. So what is the research focus of my group? One of them is to work on new network architectures. And this has been an effort that's been going on for more than 10 years. NDN, named data networking, is something that is built inherently to deliver data and to manage computations. And of course, I could give a whole talk on that. But that's been one of the future internet technologies, architectures that is still around after a number of years. In fact, that was one of the NSF's main initiatives 10 years ago, is to look for new architectures. So that's actually become more mature and implemented in many cases, including in my group. We are interested in optimal caching routing algorithms, data distribution with optimality guarantees, how to do that in general networks with arbitrary topology and demands, adapting to the demands, and done in a distributed way. Beyond that, we're interested in workflow optimization, container orchestration algorithms, which don't do just the caching, but also manage the computations jointly with the data delivery. So this is extremely important for edge computing, and we want to do it for general. We've already done much of this for general topologies and under adaptive conditions. And also we're doing networking for distributed learning at the edge. So the point is that traditional networking protocols are designed to maximize metrics such as throughput, delay, things like that. But these days we're interested in designing network protocols for learning objectives, such as to minimize the error covariance of learning objectives. So this is so the main message here, without going into too many details, is that we're focused on new type of networking, new network architectures, networking to deliver data, networking to manage computations, and networking for distributed learning. Okay, so now I won't go into this too much, but this was named data networking was a big effort, and Northeastern is leading the theory and algorithm development for this architecture, applications to wireless, and also we have applied it in big science projects like Large Hadron Collider, high energy physics. There's a global testbed, growing code base. If you're interested in this architecture, go to this website, and it has all of the information on the paper standards, testbed, code, etc. Okay, so yeah, let's not go into all of this, but it has many functionalities which are really built for networking for data. And it has a natural extension of computation learning. All right, I just want to mention, for optimal caching, we have a lot of work that this is joint work with Tracy Ho, Strutisi Unitas, and many other people over the years. Basically, without going into the details here, we're interested in, if you have a set of content, if you have arbitrary network topology, how do you optimally decide on the caching locations? And where do you store what on the network in order to meet the demands according to some metric? And the metric could be to minimize network cost, to minimize delay, et cetera, to maximize throughput. This problem, very fundamental problem, actually was kind of open for a long time because people either had heuristic algorithms for general topologies or they had optimal algorithms for very limited topologies. And so we are actually able to make a lot of progress here. So one of the things we developed was so-called VIP, and this was one of the first algorithms that did joint routing and caching for arbitrary topologies, and it maximizes the user demand, has a lot of great performance. This appeared some time ago, and the okay. So I thought I had a performance plot here, but okay, that's not in there. Another approach was done with Stratis here, and this was using an approach based on a convex relaxation approach which gives optimality guarantees using stochastic gradient ascent. And this was extended to jointly optimal caching and routing and many other extensions on queuing, cost, and congestion control. The point is that we're able to develop all kinds of algorithms for optimally delivering data over arbitrary topologies under many different kinds of costs. So this is extremely relevant to problems like edge computing, where you want to cache close to the edge, and this is of a lot of practical utility. Beyond data delivery, we're also looking at how to manage computations. So you might have a situation here where you have small cells or you have servers that are able to do computation and have storage capabilities. And so the question is, how do you jointly optimize how to route the computation requests, how to schedule the computation, and do the data caching at the same time? And this can actually be solved. We developed something called DECO, which maximizes the throughput of a distributed computing network, which is distributed adaptive. It also could handle data inputs. And we have extended work on this. This goes beyond data delivery to handle computations. That's why you can basically think of this as optimal container orchestration combined with caching. Okay, so this is something that, again, is extremely useful for edge computing. Lastly, I just want to mention the recent work on networking for distributed learning. So you might have a smart cities application in which there are many different kinds of sensors deployed across a large area. They're collecting different types of data. But then you have different learning and inference tasks like vehicle tracking, traffic estimation, etc. And these learners are trying to pull different data potentially from different sensors, and they might even have overlaps. How can the network facilitate these learning and inference tasks over this in order to optimize some learning criteria? So this is a different kind of networking. Our objective is not throughput or delay, but rather learning objectives. So so sensors are dispersed. They're generating streams of data, and learners are data consumers, which wish to train models over the received data, and different learners may be interested in different data, but overlaps exist. And so how should network resources be allocated to facilitate these learning tasks? Here, turns out, this is not an easy problem. It's non-convex, but has nice structure. And we developed some polynomial atomic approximation algorithms to find a solution that has an optimality guarantee. So this is a good example of a situation where networking is designed for new objectives that evolve from learning. All right, let me just conclude here. I think that we're in a new age of networking that really focuses on delivering data, scheduling computations, and how to manage and how to facilitate learning. So there's a movement to the edge, right, for various reasons, and new business models are being developed at the moment. NDN, named data networking, is actually a very natural architectural approach to this new landscape. And in fact, all of these things that I just talked about were in many ways motivated by this NDN architecture. Had it not been for NDN, I probably would have looked at these problems. We have optimization of caching of data-intensive and of computations in data-intensive computing networks, and networking for distributed learning. I think these are very much the new problems that are of importance. So thank you very much, and look forward to chatting more.
All right, welcome back, everyone. Let's get us started with our next session, which is going to be on industry engagement and models. Let's see. Perfect. So I'm not going to take too much time, just a recap of some of the facilities and resources that most of you are already familiar with. I'm just going to do a quick recap. starting with the notion of Open NextG R&D Center. This is what we launched, as Tommaso was mentioning earlier today, in last summer. This is primarily funded by DoD, Office of Undersecretary of Defense, the RNE. It includes 4,600 square feet space at Burlington. This is primarily going to be a shared space for researchers, entrepreneurs, and we have had some interest from industry collaborators that they wanted to have access to that space. That's co-located with Coliseum, anechoic chamber, and a bunch of new test beds that we are putting together up there. This is, again, just a quick look at all the industry collaborators that we have as of today. The list is growing for sure. There are different tiers of the industry engagement with the Institute that I'm going to talk about that briefly today. This is, again, an exemplary list of all the facilities that the Institute and the Open NextG R&D Center do have access to. As you have seen all the presentations in the morning, it will go all the way from sub 6 gigahertz all the way to above 100 gigahertz and terahertz frequencies as far as the radio propagation concerns. And of course, we have AI computational capabilities. At this point, we have, I guess, a handful of the state-of-the-art DGX A100 from NVIDIA, thanks to the supports that they have been doing. We are part of the FCC Innovation Zone. There's only a few of them nationwide, both at Boston and Burlington campus, so that enables us to do research over the air, and that's actually what we have been doing quite a lot. There's Coliseum, Arena, we talked about that. We have the drone cage, the list goes on. You have access to power. And it's expanding very quickly and fastly, both on the equipment, facilities, the space, and also on the researchers, engineers that we are recruiting, as well as the industry collaborators who are joining the Institute on a daily basis. This is a quick recap of two different models that industries can get engaged with the Institute. Again, many of the people who are here in this room are already in one way or another already contributing to this ecosystem. But just to recap, one of the models on the left is the standard membership model. So the industries can come here and become a member of the Institute. It has 4 different tiers as of today. The bottom 2 ones are for smaller businesses, and that will give them access to all the facilities and resources and the shared spaces, including testbed facilities such as Coliseum. You can get membership and use them. The upper 2 ones, that's the part that you will start getting access to full-time researchers at the Institute working on a project. The first one will come with a single PhD student and PI time. The second one, the top tier, will come with 2 PhD students and also PI time. And of course, if there is need for a couple projects, that's also, we can expand on top of that. The one on the right is a different model. Some companies prefer that version. That is essentially a scope of work that in a meeting we agree on a scope of work on a specific project or product. That's a binding contract, and then based on the scope of that project, we can define how many resources are needed and what facilities that the specific project needs access to. Again, that comes with all the good stuff, the facilities, researchers, and whatnot, the space that we have in Burlington, that comes with that as well, and you become a consortium member of the Institute with that other version of the engagement. Very quick, I'm going to do 1 sentence per slide. This is just an example of the great research that we have been doing in the past few years that has been enabled with our industry partners. Starting from Keysight, the idea here is to put together the world's fastest real-time terahertz link for the first time. With Raytheon, we have been working a lot on different types of AI applications in wireless telecommunications, primarily, of course, focusing on secured wireless telecommunications. With MITRE, we have been working on jamming and anti-jamming smart systems. And of course, there are regulations on jamming systems, so there's this interest to use emulation platforms so that you are not actually interfering with the actual radios out there. This is an effort that we have done with them. Again, there's a poster later this afternoon that you can see all the details of all these different projects. This is Meteor that is integrated with Coliseum, an emulation platform. With Viavi, as we speak this week, we are doing this measurement campaign with them. The idea is to put together a real-time digital twin with AI-enabled ray tracing systems. That's the effort that we are doing with them. With InterDigital, over the past few years, we have been working on, again, so many different applications of AI in wireless telecommunications. These are just a few examples on radio fingerprinting. Those are two of the products, Deep LoRa and Science CRF. That's where you can fingerprint devices by the impairments of the hardware just using the signal that they're propagating. With NVIDIA, the effort has been on enabling 5G and O-RAN testbeds, again, primarily using NVIDIA aerial physical layer and integrating that with the facilities that we have. With Mavenir, the idea is integrating the O-RAN intelligence with network simulators. Again, this is a work that has been recently published. With Dell, the idea, again, is enabling different AI applications in O-RAN, including slicing and XApps and whatnot, again, utilizing network emulators. And with Qualcomm, two separate topics, but related. One of them is compliance testing on 3GPP on Coliseum. Again, the concept of digital twin that we have been talking earlier in this morning, that's one of the concepts that is being used to create those digital twins, and also on O-RAN security assessment, again, utilizing our network emulators. And with Red Hat, again, the idea here is many of them are AI applications with O-RAN. This is not exclusive, so with Red Hat, we have been working on, again, zero-touch RAN and spectrum sharing systems on O-RAN. And that's it. This is just an example of 10, 12 of the projects that we have been doing the past few years, and we look forward to more of these projects with you guys. I just wanted to do a quick recap. And with that, we are going to have two more parts to this session. The first one is going to be a panel on commercialization and entrepreneurship. Ted Worth is going to moderate that panel with 4 of our great panelists that he's going to introduce. And after that, we're going to have 4 short startup pitches. Those are the spin-offs of the research labs at the Institute. And right after that, we're going to recognize a couple of them who have been doing a great job. Right, with that, I'm just going to hand it over to Ted.
Thank you. Can you hear me? Okay, great. Oops. If they can put the notes up there, great. Got it. Okay, great. Hi, everyone. My name's Ted Worth. I'm the executive in residence at the WIoT Institute. That means I tend to work with most of the researchers who have commercialization ideas, although there's a whole bunch of other resources on campus to help with that. As we just mentioned, we're going to have a panel in just a second to talk about investment, and then you'll get a chance to see some of the real companies that are coming out of the Institute. As most of you know, the WIoT is committed to advancing commercialization, bringing research to market. And the number one step to make that happen is connecting with industry so that there's collaboration on what is needed in the real world, and the real world can find out what's going on here at the Institute. There are other programs going on. You just saw some that Pedram mentioned. There's other parts of the university that are helping. It's a big effort to try to push forward the commercialization. Why is it important? It's always good to go back to that. I just wanted to talk about this before our panel. The world has lots of needs. It's got a world of needs. There's also a lot of opportunity. And the research being done in this institute has the ability to impact technology, industries that are going out and being distributed over the next 10, 15 years. I just want to talk about one example. This is 5G, which tremendous amount of work going on here at the Institute, really swings the needle out in industry because over the next 7 years, it's expected that there's going to be an additional 400 billion in our GDP and probably on the order of 700 to 800,000 jobs created. It really behooves us to do a good job getting these technologies out there. While it may be challenging to measure positive social impact of 5G, we also know that it's going to increase social engagement and improve health and security for almost everyone. So that same point can be made for the other technologies being used here at the, being researched here at the Institute. 5G, robotics, Internet of Things, artificial intelligence. All right, so most of the researchers here are familiar with funding options associated with research. They've been working in research for the last 7-10 years, getting ideas closer to market. We want to answer the question of what happens when you want money to commercialize your research. And that's where we have a panel of investment professionals. Please come up. And if you can identify your pictures. The intent is to be in front of them, not mix it. Each of their firms support commercialization of research. Each of them do it in different ways. So the purpose of this panel is to help the people in this room, all of us understand when you want to commercialize, what do you need to do, what do you need to know when you start going down the funding path. Okay, we're going to leave it on this slide. So the anecdote I'll give you is every single venture that I help that is involved in deep research, they come to me and say, I have a great idea. I want to get funding. Why is it so hard? Everybody else is getting it. And the answer is there's some very good reasons why that's true. And so I'm going to put the panel on the spot with the first question. This may be the only question we ask because there's a lot of depth to it. And that question is, what are the reasons it's so difficult for a research venture to get funding? And Myron, since you're front and left, why don't I let you go first?
Great, thanks, Ted. So happy to be here. I'm the Director of Commercialization for Northeastern's Center for Research Innovation, which is our tech transfer and venture development office. So I work with many of the researchers and some of the companies that you're going to be hearing about. But we are responsible for protecting and commercializing innovations that come out of Northeastern research that are owned by Northeastern. And we do that through licensing and through supporting spin-outs. And so in some ways, we are the first investor, though we are not a venture investor like some of the folks on the panel, but we're the ones that are putting up the funding in order to protect and to file patents. We also have a Spark fund, which is a grant fund of $50,000 grants to further the development of technology. But at the end of the day, our job is to really put our technologies and our spin-outs in a position where either they're fit to fund by Russ and Stacy writing a check to them in order to fund their ventures, for Mark to accept some of our spin-outs into his program of further development, or to get an industry partner to basically take a risk at taking some university technology and investing through a license in commercializing it. So
Myron, I apologize for interrupting you. I did want to do introductions.
All right,
so that's
I'll
our
stop
first
there.
introduction, and we'll come back to the question. I apologize to the panel for that. I do want each of the panelists to talk about who they are, the company they represent, why it's in business. I mean, all of them are investing in research, but they're very different and have lots of similarities. Maybe talk about some of the programs that you have, if there are some in addition to funding. So again, with apologies, Stacy, she is the person running all investments at Mass Ventures.
How do I turn this on? It's on? Oh, it is on. I do not run all investments. There's 3 investors at Mass Ventures and also a president of Mass Ventures who helps us with those investments as well. So Mass Ventures is your state's, or the state of Massachusetts, strategic venture capital arm. When it was founded in 1978, it was the first such quasi-public to do so. Now most states have one. So we're one of the oldest venture capital firms in the United States. We run what's called an evergreen fund, which means the shorthand is very patient capital. And we invest in early stage startups with in the same way a normal, a regular venture capital firm would. We write these checks, and we are take some shares of the company according to the term sheet of the deal. We do, just because it says state government, I should note that the state has a host of investment vehicles. There's also loans and equipment loans and various grants. We also administer a couple of those grants. Our biggest one that we work on every year is we administer one called START, which is we push out $3 million a year to SBIR Phase 2 winners. So that's another way that we support university spinouts and deep tech in the state. And so, we're very technology, deep tech focused. And then my background personally is in material science and in industry.
Great, thank you very much. Let me introduce Russ Wilcox, a partner over at Pillar Ventures. All of these people are from the Boston area, so Pillar's in Boston. Take it away.
Yeah, hi, I'm Russ Wilcox. I'm a partner at Pillar VC. Previously, I was an entrepreneur for maybe the first 20 years of my career. I started 3 university spinouts, one of which was e-ink. We made electronic paper. And then I did another in energy and another in immuno-oncology, so life science. And then at Pillar, we have $350 million under management. We're typically writing your very first venture capital check. You might have had some angel or some other support, but it'll be your first VC check. And it's typically from us sort of $1, $2, or $3 million in a round that might be $1 to $5 million is a normal range. And at this point, we have about 80 companies in the portfolio and half of those university spinouts. So looking forward to today's topic.
Thank you. Okay, and then let me introduce Mark Castleman. And I don't know if you're new to the area, but the venture, the Intel Ignite, is relatively new. Maybe you can talk about that.
Yep. So Mark Castleman, I'm the managing director for Intel Ignite, which is Intel's deep tech accelerator. And I run the U.S. program, and so I'm new to Boston.
Okay.
I'm from the Bay Area, came to a small school on the other side of the river, and barely finished. So taking donations later if you guys want to support the cause. Anyway, so Intel Ignite is different than Intel Capital. We can talk about both. As a background, I was a founder, raised money, built companies, crash burn companies, sold companies along the way, and then got into corporate, and then also large scale fund, global family office, and then many VC funds and a fund to funds approach. That may not mean anything to you, but my point is that you see a lot of things. So when we're talking about what does it take to raise capital, sadly, there's not a single answer to this problem. But there are things that you can know about each stage that you're in, perhaps, or each category that you're in, and how people think about investing is probably exactly the opposite of what many think. So understanding the other side of the table is probably the most important aspect of obtaining capital when you're in market looking for capital.
Thank you very much, Mark. All right, so back to the question. Myron, what are the reasons it's so difficult for a research venture here in the capital of financing on the East Coast to get funding?
So I think one of the challenges that we see is, how do we elevate the sort of funding fitness of both the deep tech spinouts that we've got and also sort of faculty inventor entrepreneurs. I think that the skills that you develop as a successful academic is that you're able to raise funding from the government, from industry sponsors. That doesn't always translate into being able to raise money from folks like on this panel who are institutional investors that have different criteria. And so I think that, unfortunately there isn't like a LinkedIn training program that you can take that will turn you into a fundable entrepreneur. And so I think, the advice that we try to give is to take advantage of a very rich ecosystem, both here at Northeastern and throughout the Boston area, of really trying to understand what this journey that you're going to embark on really involves, and also take advantage of access to folks that will be writing those checks to try to understand what is it that they're looking for. So I think that one of the challenges as a university, and this isn't just Northeastern, but in any university, is how do we work together to try to take these wonderful technologies in sometimes difficult markets like telecom and is sort of deep tech, where if you're doing a SaaS software company, you might be able to get away with a couple $1 million and get to revenue, but these are deep tech companies that are going to need capital. And so I think the challenge really is how to align the capabilities with the technology to be able to succeed.
Stacy, do you have an opinion on why it's so difficult?
I have so many opinions. He's teasing me. Well, if you boil it down, in venture we often talk about team, technology, timing, and enclosed in timing is market and market size. So I suppose the good news is for all of you here that deep tech is really an area of interest for investors in general right now. So in some ways you have a leg up, but when, what Myron was saying about getting ready and having that team, being a fundable team, and as the investor, you're like, well, do I want to go on this journey with you? And do I want to do it with these people? And do I think this team can lead the way and get there? It's very hard to assess. And then sometimes you're also thinking, can I help this team? Like, do I even have the requisite knowledge to be helpful in any way, right? And then the technology you guys probably have, like your IP moat, like just what's going on, what's novel? Is this really novel, or is it like, a Me Too thing? And we'll figure that out. We'll do our best to assess that independently. And then the timing is, again, just the timing. Are you early to market, late to market? A lot of ideas fail because they're early. And then obviously many fail because they're late. And then market size is usually the biggest predictor of success, actually. Is your market really big? But of course, how are you going to get there? So that's a little overview. I'll let Russ add some really good color to this.
I'm in sync with all of that. I think, Ted, what if let's say people from Northeastern are saying, I've got ideas, why can't I get funding? And I've been watching startups in the Boston area for 25 years. The biggest thing that separates that, if you want to talk about like on an institutional level, is whether people care. And there are many academics in the United States who just want to do research and really have no interest or expectation that they can do a startup. There's very few that actually care and want to do startups. And you'll discover that they will actually aim their research at things that are well suited for startups. And, it's sort of like, if you're going to go on vacation to Sweden, you might like learn some Swedish, or, what I'm saying, like when you're talking to startups and you're talking to investors, from the point of view of an engineer or an inventor, it's a different language. And you either have spent several years thinking about that, trying to learn the language, trying to understand what makes a good startup, and is worth millions of dollars in a decade of your life to bet on. You've either thought about that or you haven't. It's really hard to fake. So I think the biggest thing is just desire. And I'm sorry, it's not like we're not going to learn one phrase, one size fits all advice here in this panel. We have 1,000 phrases and 1,000 pieces of advice. But it really just comes down to whether you're willing to put in the work and whether you actually care, whether the research you're doing is translatable in a startup context.
All right.
Yeah, I'll take that. I like that because if you think about what you're doing in the lab, you're solving the hard problem. And one of the first times that I was introduced to that concept is I sold a company to Alcatel-Lucent, and I became the entrepreneur in residence at Bell Labs. And I met 1,000 researchers solving really challenging problems in the lab. And almost all of them were afraid to see the impact of that in the marketplace. And so solving a problem in the lab is very different than solving a problem in a human being's life. And so the investor that you go talk to sees thousands of deals every year, and you walk in, you say, look at this really hard problem that I've solved. And the investor is saying, what does that mean? Great, congratulations. If you want a pat on the back and get a pen and get an award, that's not venture. That's not culture impact. So you have to also understand that capital is fungible. It goes anywhere. It goes where it's best suited. And so when you pitching or asking for money, what you're saying is you have the best vehicle to see that capital have impact in the culture than any of the other 1,000 deals that VC is looking at. And so that's a very different equation. So if you want to solve the hard problem of coming to raise capital, look at what the life of the investor is as they examine the deals that they examine and why they examine them the way they do. That's a super hard problem. You could probably write a great book if you could figure it out, but you would know, okay? And so to me, it's really about understanding what impact you're actually having other than, kind of patting yourself on the back. And I think that when you are able to speak the language of how your stuff, your solution works in the culture, you will be able to get people's attention. And the last thing I'll say on that, Google did research. They researched, I think, 1,000 of their companies that were going through Google startups. The number one cause of failure was the team. Number 6 was the tech. And it was orders of magnitude higher. Over 55% of teams failed because of team, or of companies failed because of team. And it was like 7% because of tech. So if you're leading with your tech and you think that's a path to the solution, I invite you to kind of rethink it and see what's actually happening.
So good observation about the teams, and that's come up now a couple different times. What advice would you have about how they should set up their team? What skill sets do you think are missed most when you're talking about a deep research company?
Yikes. Did I just say yikes out loud? Okay, I've kind of answered that a little bit on my last, so I won't go into it further. I would say that the thing that's missing from a deep tech team is realizing that what will make you successful is not that you're a deep tech team. What will make you successful is that you understand what your tech means in the life of other humans that have no idea what you're talking about. So that is a different muscle than being really good in your lab. So when I have founders approach and say, oh, I have $9 million in funding, I say, what type of funding? Say, oh, I have $9 million in grant money. Say, that is not a third party telling you that you will be successful. That's a third party telling you that whatever you might be working on might eventually become successful in someone else's life later. A professional investor looks at it different. So if you come into me with $9 million funding and no other funding, in my world is zero. So you have to think about what does it look like to be in the future. Think future state versus like what you saw today.
So Russ, along the lines of finding an investor, there are lots of investors out there, but usually not many that meet the needs of a particular company. Do you have any? Can you describe more what type of companies should come to you and what criteria people should be using when they approach any one investor?
Well, I think the first question, you would start by saying, how much capital, what's my market I want to go after? And is it a very big market or is it a niche market? I make no value judgments. I think if you want to start a $3 million company, that actually can be very good for you as a founder. So that's fine, but it won't fit venture capital. So you look at what customer's problem am I trying to solve? How much capital do I need to get and build that business? And then is that a good investment, and who would like that kind of investment? If you think that you're going to build a business with at least $100 million of profitable revenue, and it can have an exit that's like an IPO or $1 billion exit, it can be a unicorn. You envision yourself ringing the bell on the New York Stock Exchange, ding, ding, ding. If you think that's you, then you want to come see venture capitalists, because that's all the venture capitalists care about, finding finding that. The whole career of VC is boiled down to which unicorns did you fund, right? Everything else is, it shouldn't maybe be this way, but that's all they really care about. So if you're not one of those, know thyself and don't waste your time. You might figure out, oh, I want to start a restaurant. Well, who else in my community has backed restaurants, right? Or I want to start a small lab service company to do specialized testing. It's going to be a $5 million business. You might try to find some people in the industry or some local angels to give you the $1 or $2 million so fit and connection. If you're in the VC, start with Pillar and it will go well from there.
So Stacy, how about you? What do you think is? I don't know if you're trying to build unicorns or you have other objectives in mind representing the state.
Well, that's an interesting point, and that really gets to, just to touch back up a tiny bit about that issue of team, and this really matters for your venture team as well. Just network hard. Network really hard. You can't afford any dead weight, like zero, when you're a startup. So look at your look at your gaps carefully. Do ICOR, and choose carefully and network hard. You want people with a good Rolodex. Also, your investors, if possible. It makes a huge difference. And now your question was about other things that we look for. So as a firm, Mass Ventures has a different personality than Pillar, right? Who can invest internationally. We're limited to Massachusetts. We'd love it if your company was in Pittsfield or New Bedford. We love university spin-outs, but even though MIT puts out, 300 startups a year or a day. I don't know. We love UMass Amherst, right? So we always are trying to spread the love, spread the love in Massachusetts. So that's sort of our personality. We love female founders. We love minority founders. So every firm has its own goals and personality too. So sometimes no just means like, you're not a fit for us, but it has nothing to do with what's really going on with your company, right? Or what the full promise of your company is.
So Mark, along the same lines, you are part of Intel. Perhaps you can talk about what is the outcome. Are you trying to build companies that have different flavors than we just heard about?
Well, okay, so think about Intel. Intel is a company that makes chips, but we have tons of other tech. It's one of the largest software companies in the world that makes actually very little revenue from software. We have tens of thousands of software engineers, so it's kind of weird to think about Intel's software company. We also have Intel Capital, which is a fund that invests off the balance sheet from Intel. They invest about $500 million a year, which is a lot of money, and about 30 to 40 new investments each year. And then they have the additional investments that they've been tracking for years that they continue to invest in. Generally, the investments from Intel Capital are strategic to Intel, to the business units of Intel. So typically when you see a CVC, a corporate venture capital, they're going to invest in things that are kind of like in the same lane that the company is pursuing. Ignite is slightly different. So we're an accelerator. So we're looking at companies earlier, but not formative. So we find companies that are pre-scale. They've sort of figured it out a little bit. Russ may have invested in them. Mass Ventures may have invested in them. They haven't quite become scaled grown-ups yet. So we get involved because maybe we might want to buy them. And Intel does not buy formative companies. We only buy companies that are already grown up. So if you want to get acquired by a big company, become a big company. Because we don't care how big the check is. That's the weird thing about Intel. We only care about not losing. So we will only buy companies that are grown-ups. So you think about how the capital is formed and why people do the things they do. And I think that's probably, hopefully informative to you. But, we'll look at just about anything. I have health tech companies, I've got molecular AI, I've got a space tech company, I've got a brain implant company, I've got, model deployments, I've got model optimization, I can go across the board, and then I might be the beginning of your network. So back to Stacy's point, find the kind of formative networks that can get you to the next networks, and then think of it as a journey.
Thank you. I want to make sure it's open to all of you. If somebody has a specific question they'd like to ask, I think there's a microphone. I can't quite see it here, but there should be one in the middle, and there's one over here. Please just grab it and wave, because I'll miss it completely. So keeping to go forward. This is a research group. As a research group, they're developing IP. And so Myron, a question I'd like to start with you and then hear how the professional investor side looks. What is your view about how IP is valued relative to a commercial entity?
It's a great question, Ted, and I think that you'll hear different perspectives from different people. On one hand, it is sort of table stakes, and it's always a checkbox that investors are going to look at. And one of the reasons is if they're going to be putting in tens or hundreds of millions of dollars worth of funding, you do want to make sure that there's some sort of a moat or some protection so that what it is that you're developing is not going to be copied or utilized. But it's just one piece of the puzzle. I think IP is important. We try to do a responsible job in filing patents that make sense, that are going to assist in, when we're sitting across the table from an industry licensee, they're going to want to understand why they should be paying a license fee in order to utilize that technology. But I do think that there are a lot of other aspects that add value to the IP, which is, have you built a prototype? Have you thought about what the applications are? Have you sort of driven it to the customer experience side of things? So a patent is a piece of paper with, I think these days, 8 digits on it. And it's really up to the entrepreneurs and the inventors to turn that into something that's valuable.
Great. Anybody else want to comment on this? I'm really interested in what how
As
it's valued.
a founder, I never really benefited from IP during the journey I was on. It was always at the beginning, super important, at the end, super important. In between, it's not going to make you or break you. It's basically, think of it as like a force multiplier in certain contexts, but it's never the reason that any investor is going to say, oh my gosh, you have these 10 patents. I was waiting until a company walked in with these 10 patents. Here's $10 million. That just doesn't happen. If you walk in and you say, I am pursuing this monumentally huge marketplace, and I have the ability to defend whatever portion that I collect for myself, because when you go into a space, the space doesn't say, oh, welcome, take everything from us. They push back on you like antibodies. So your patent is basically part of your defense against that, or it's your sword. So you will find that out at the beginning and end. In the journey, it's going to be your team. It's going to be your ability to execute. It's going to be your ability to find customers that have the problem. It's going to be your ability to hire people. All of those things matter. So this is just my personal view. It's sort of entry point maybe interesting, and exit point kind of multiplier on potential scale valuation.
I'll chime in that we're often working with Myron in the technology licensing office, and we do pay quite a bit of attention to IP at the beginning. And then I completely agree with Mark. IP is something you have to invest in early, but it only gets valuable in the end game when you're selling your company, because only a big tech giant really has the money to enforce a patent, because it's a huge lawsuit to actually enforce it. So you're really creating, but unfortunately you have to spend the time and effort early. So we look at two things. First of all, we want to know, if you've got this great invention, can it be protected? And really you need some way, if your company succeeds, of preventing copycats. It could be a network effect. It could be some unique channel, but often for things that are spin-outs, it's IP patent portfolio. So we'd like to know that you actually have the ability to get that and that you have a license. And Myron's smiling at us from across the way saying, yes, I'm going to give them the license, because we don't have a company without that. We also look the other direction, which is defensively, which is called freedom to operate. And that is a question of whether someone else, maybe there's a rival research lab across the country doing similar work, and actually they filed their IP before you, and it takes a couple years to see what patents result. we might not be able to get good patents, or they might be able to have a patent on something else. And one of the big differences between a company view of IP and a licensing office view of IP is that for Northeastern, it's very important they get at least one patent so they can block other people from using the technology. So if you imagine a car, as long as you can patent a car engine, you can stop the car industry. So that's what they need. But if you're an entrepreneur and you want to sell cars, you need to not only have your own patent, you need to have nobody else have a patent. So you need to have a source of tires without infringing on someone else's patent, and a source of, windshield wipers, and like everything that goes into your product, you need to have a way to ship it without infringing someone else's patent. So that's called freedom to operate. And maybe not at seed, but certainly in the early stages, we're going to take some real time before we spend millions of dollars, make sure you can get all the way to market with a complete product without being held up by someone else who can sue you with their patent.
Great. Okay. And one last question on the value side, Stacy, is there's all these examples of companies that go out and raise $60 million, $120 million valuation, and they're going to grow like crazy and become that unicorn. How do you value the companies that come to you from the research environment?
That's a great question, because valuations have changed drastically in the last year and a half. So it's extremely hard to value a company, and in general, we do a boilerplate, and we also just see what the market will bear. So it's incumbent on the founders to try to get multiple offers, and if you can't, we will just offer you something that we think is fair, and that's going to be, if you're doing a $2 million raise, then the boilerplate is that's going to be, the $2 million is going to be 20 to 25% of your company for that first round, like a seed round. So it would be $2 million, and your company is valued at $6 million pre-funding and $8 million post-funding. So that would be actually a pretty typical deal right now. And it's fine, and it gets you going.
Go ahead, Myron.
I was just going to ask, do you find that valuation is something that people agonize over? Is it something that they shouldn't agonize over as much? I mean, what's been the sort of...
Generally, the advice is don't agonize over it. I totally understand. We've all been there, agonizing over it. But generally, the advice is just you have to wear two hats. So you have to think like a founder and a CEO and a technologist for many of you, and a marketing expert. But you also have to think like a shareholder, and just always have that shareholder hat on, and just take the deal that you think is best for your company. And if you're successful, the company will grow so much in value. And even if you get sort of diluted in that process, the board will be motivated to throw more shares to you to keep you happy if you're doing a good job. So there's a lot of mechanisms that come into play to keep things comfortable and fair. The hardest thing is just a down round. And so that's where it gets sort of tough. There's definitely a bunch of companies going through that right now because of the change in valuations.
And a down round is one where the company's now worth less than it was at the last investment.
Right. So you may have had a $90 million valuation post-closing on your last round of $20 million. And now someone's coming in, and I know a company that's happening to right now, saying, nope, you're valued at $70 million now. So you just on paper lost $20 million. So that's equally tricky.
This is very much the right way to look at things. I have an oddball way of looking at it. Well, I'm going to invert the problem. I think it's wrong for the founder to say the valuation is, it's a number, and a lot of you come from schools and classes, you get graded, and so it's a number, and every entrepreneur sort of looks at that number and says, oh, it reflects my value, or it's something about my company's value, or maybe to reflect the discounted net present value of all the future cash flows. No. Here's the inverted way to look at it. It's all game theory. See, we know you'll give up 20 to 25% of your company to get the cash you need. We know that because it's happened thousands of times in history. And we know, therefore, that the dilution of the seed round will be 20 to 25%, because that's what always happens. Sometimes it can be like up to 50% in bio if you're doing something really risky, or maybe it's 20% or even 15% if you're doing that. But basically, it's going to be 20 to 25%. So actually, your valuation is completely under your control. It is a function of how much cash people are willing to risk. And if they're willing to risk $3 million, your pre-money to give you a 20%, it's going to be $9 million. If they're willing to risk $30 million, your pre-money is going to be $90 million. It really comes down to what is the correct risk to take? And if you are able to do a lot of the research work on understanding the customer, the path to market, not just the technology, but the whole company, and you're able to attract a terrific team, the perception will be that there's less risk, and this is further along, we can write it a bigger check. We can do a $5 million seed instead of a $2 million rate seed. And guess what? Magically, you are going to have a $20 million valuation. So it really is, it's not the opportunity or you per se, it is the readiness of your venture to accept big amounts of risk that defines your valuation.
I'd like to add, because I think that's perfect to bring in the word risk. A lot of people think venture invests independent of risk. And it's just not true. What Russ is saying is like the signal of the risk that you are bringing to the venture capitalist is embedded in the dollars that they're willing to give you. And then that becomes to sort of roll that up to figure out where the equity is going to go out the door. So most times the founders come in from the equity side. They obsess over percentages. They obsess over. So I can give you $1 billion valuation if you like, but I'll own everything about the company in terms of the features of the rights that I get in my stock. So I'll give you $1 billion valuation if you want, but that doesn't do you any good as somebody who's actually trying to grow value and run the company. So what I'm saying is that the mechanics of how all of that works is understood when you think about the investor side of the equation, which is risk driven. So if I have a certain amount of capital and I can put it into 10 companies, I'm going to look at what is the probability or what are the sizes across all those. If I'm a power law theory guy, everything has to go 100x because everything goes to 0 or 100. So I need to have one deal that pays 10x across the fund. Does that make sense? So I don't even know if you guys have heard about this, but I would look at venture economics and understand, why does somebody write a $3 million check? And what is the risk that your firm brings? Deep tech, very risky. Why? Takes a long time. Markets aren't always developed. Risk is up. It's hard to get $60 million. However, if you have a $100 billion market in a moated tech that you have demonstrated traction, that I can calculate the velocity of that growth, I could write you a $100 million check. So I think it's perfect to think about the investor mindset and don't obsess about percentages. You'll win it back when you win your market.
Great. That was a super answer.
I love this talk about risk too. And I would just, keep in mind that, and this is going to sound so dumb, but the number one thing you can do to de-risk your company is to just bring in revenue, and not grant revenue, but like customer revenue. And maybe that's a non-recurring engineering. Maybe that's an MOU with a tiny bit of pilot money. But the number one thing we look for de-risking is revenue. Because get your own money.
Great.
By the way, there's this concept called do the things that don't scale so that you can do the things that do scale. So what's your future state mindset of what you think this business is doesn't have to be the first thing that you do. You can take a step in a small market that demonstrates kind of all the mechanics of your big view. Because if I can see you solve something in 10 steps in a small space, you've just de-risked for me your ability to solve those similar 10 steps in a much larger space. Not completely, but a portion of it. So don't be afraid to get super specific in your application to prove revenue, prove go-to-market, prove your ability to execute across all those things, many of which have nothing to do with your tech. And then you can say, okay, now I want 60 million. Why? Because you gave me 3 and I crushed it. And so versus saying, man, I'm going to take over the world, give me $200 million right now. Some people do that, which confuses the entire space. But if you look at the individuals that do that, there's another story going on. It has nothing to do probably with the tech that they're working on.
Great, thank you. One last question. I know we ran out of time maybe 5-10 minutes ago, but this has been really interesting. The economy is a challenge. If we could just go right down the row for your business or your type of business, you know, what you do, or your group of companies that do what you do, what's happening? Are you cutting back investing? Are you adding investing, pedal to the metal? How do you characterize the current environment?
We're pedal to the metal. I think it's a great time to be an investor. Did I cut you off, Myron? No, go ahead. I'm sorry. We're pedal to the metal. I think it's a great time. And the companies that we've invested in are actually doing kind of well. So despite the headlines of what's going on, for the most part, I think our companies are actually, our portfolio is doing really well in the current environment. There's been a lot of, there's just a lot going on in the nation. And the nation's busy and working, and so I think it's hard times, but it's good times. All systems go.
Okay,
I'm an optimist.
One pedal to the metal. Myron?
I think that, you know, the impact on us, obviously we don't have a fund, but it's just we do venture development with the spin-outs that we're working with and the faculty entrepreneurs and researchers. And so I think just having a more realistic view of where are those pockets of investment and probably having a little bit longer time horizon relative to, you know, I think things are you're gonna have to, I think the bar's been raised as to what qualifies for a fundable opportunity. And so even though there's money and it's pedal to the metal, I think people are being a little bit more cautious. And so our advising the spin-outs that we've got to be prepared for, you know, maybe a little bit longer horizon.
Okay, so I'll take that as status quo, pedal to the metal. Russ?
Well, we're pedal to the metal. We're deploying cash as fast as we find good opportunities. And I would agree that now is a good time to start a company. By the way, the capital markets today are of almost no bearing to you because you're going to sell your company, which really the only exit matters. You're going to sell it 5-10 years from now. So who knows? Like, and your first capital raise of just $1 million or $2 million, like it's just not material. You know, you are a cork bobbing on the ocean. So like, what do you care? It's all local conditions that matter, not the overall title table or something. So basically, yeah, it's less VC this year than there was during COVID, but that's because the government dumped a ton of money into the economy during COVID, and we had this avalanche of cash. The activity level is much lower than it was 2 years ago, but it's still at like a decade high, you know, other than that.
Yep.
So there's still plenty going on. The tech companies have let loose of a bunch of talent. I think the input costs are low. So it's actually a great time to found. I agree with Myron that if there's a little tendency right now, it shades toward doing bigger seed deals than before. People kind of want to have like industrial strength seed stage startups. So they would rather write a bigger check off a more complete team and something a little further along. And so the bar is a little bit raised harder, but then when you get over the hump, you're going to get a bigger check. And I think it will, I really think if you've got a fundable prospect, there's plenty of cash out there and you shouldn't worry about it. But if you don't have a fundable prospect in the past, you might have run across some, you know, random person who would fund you. Now it's less likely.
Yeah, I'll add to that first-time founder teams are definitely having a challenge because the investor is looking for this kind of more senior mindset because they tend to weather difficulty better because they've seen it before. Third-time founders are sort of the most de-risked if you think about what happens in a difficult marketplace. So that's great for us that are older. You know, you kind of walk in the room like, yeah, I've done this a couple times. And the VC's like, whew, okay. But then they have other issues, which is mindset and, you know, rigid and openness and all that. So you have to, it's not all, you know, like upside. I would say from an execution perspective in your company, like sideways is the new growth. Like if you can not lose ground, you're gaining ground when everyone else is losing. And I would take it even further and say, if you can give away your stuff, add potential customer to a near field opportunity in the future, you can compound that when the markets turn. So you can capture market in ways that will pay later. So if you walked into a venture fund and said, hey, yeah, the market's down and nothing's working out, but we've added these opportunities and they're legit opportunities, that's going to be an indication that even when things are not going great, that the future is looking good for you. So I think individually, VCs are looking at more the fundamentals of the business versus the space that you're in. And the good ones are going to understand that you will eventually get through this. So they want to know, why are you special? Not why is your market special? Whereas maybe in a more frothy time, it's like, oh, I'm going to put money into this category and I hope it all works out. I'm going to put it in 10 companies. Whereas now it's like, I'm going to pick one and they're going to be amazing. Tell me why you're amazing. And I'm already going to want to go on that journey. So the money and the capital are there. We're seeing companies come through that achieve that. They achieve the change in growth. That is, they figure out what the mechanics are to sell and grow. Those companies are getting funded, and so I think it's mixed, and it's definitely regional. So look, it depends, and if we had one-on-ones with everybody, we would have a different outcome for every single person. So you got to look at it in terms of your own context.
All right, let's give a hand to our panel. I very much appreciate your time. I know this is a big investment getting over here. If you can stay after, Mark, I know you have to leave for graduation in California, but if you can the rest of you can go to the panel, all the different posters, that would be terrific afterwards to lend your experience. Thank you. All right, since I know I might have gone a little bit of overtime here, there are two common ways that companies end up commercializing their tech. One is licensing to their IP to industry, and there's companies that are here that could potentially become licensees. The other one is spinning out businesses. I think I saw there's 6 different spin-outs in process. There's probably a few more, depending on how you count it. We're going to hear from 4 of them now, and these are all companies where you have researchers who somehow have managed to do a night job. They're superheroes in the evening and researchers during the day, not that researchers aren't superhuman. It's a very big commitment to go down this path, and there's a lot of energy, a lot of passion around this. I'd like to invite up Z-Touch, and then we'll just work through this list. Each of them is going to give you a quick overview of their business so you can see what has been accomplished.
Can you hear me? All right. Good afternoon, everyone. I'm Salvatore Doro. I'm a research assistant professor here at the Institute for the Wireless Internet of Things. And today I'll be introducing you to our spin-off, Z-Touch Networks. So before going into explaining you what Z-Touch does, let me take a step back and explain you how Z-Touch is born. So as an institute, we are really focused and committed in taking wireless networks and bringing them to the next level, making them more efficient, less expensive, and more intelligent. So over the years, we have been developing solutions that leverage AI to take those networks and bring them to the next level, controlling the policies of the networks, how the networks are being executed, how they are being monitored, how they're being managed, and how they deliver services to users. So across the years, we have developed a bunch of different solutions that make it possible, for example, for operators to specify an intent at a very high level, possibly in a human natural language. And then we have developed technologies that understand that intent, converts that into something a machine can understand. We have developed AI that it controls intelligently and efficiently the network itself. And then we have developed orchestration tools that automatically takes the intent that is being converted into a machine understandable format and selects the AI and the services that are necessary to meet that intent, depending on that specific traffic conditions, and bring them to the deployment. So this started in some research that we have done in 2018. It started with 4G. And then we have keep going 5G and beyond. However, this is a technology where, if you're familiar with cellular networks, that's a very closed market. There is minimal room for improvement in terms of embedding AI directly in the cellular world. However, the opportunity comes now with Open RAN. Open RAN is basically opening the cellular network domain. It's bringing AI, cloud-based deployments, and a network that is fully customizable. So, you know what? OK, now the technology that we have developed can be all combined to create a product. And the product is what we call a Z-Touch. In terms of who needs Z-Touch, we have identified what's the market. We believe that the market that is tailored for Z-Touch, especially in the early stage, is private cellular networking. Private cellular networking is a market that is extremely large. We're talking about $6.1 billion by 2030. And this is only for the software segment. So that's a very specific segment, but the market is very large. And the reason why we're targeting private 5G is because those networks, that's where Open RAN will be actually be realized for the first time. And why are we targeting private 5G and not operators? Because operators, they know a great deal of 5G networks. They know all the details how to operate them. Private 5G customers, they have no idea how to operate a 5G network. They're used to use Wi-Fi. Wi-Fi is a simple solution, very cheap, but it doesn't give you all the same performance and mobility support as a 5G network. 5G network solves those problems, brings all the performance, comes with all the customization that you want to support different services. However, it's very hard to understand, very complex, and very hard to customize, specifically for private 5G customers. And that's where we see the value of Z-Touch. We like to call it bringing 5G services with Wi-Fi simplicity. And that's what we believe it's the value proposition of our solution. So basically, Z-Touch is a product. It's a end-to-end product. We like to think of Z-Touch as a product that sits on top of the different components of the Open RAN, radio access network, core network, edge services, RAN intelligent controllers, service and management orchestration. And Z-Touch brings all the logic that is necessary for, at first, private 5G customers to express intents. And then we take care about selecting, creating the AI and onboarding the AI so that those intents can be realized. And basically, this is a technology that we have been demonstrating at different venues, at the Mobile World Congress in different locations, as well as the 6G Symposium in Washington, D.C. The technology is based on more than 12 patents. We are ongoing. We have 5 partnerships that are already ongoing. And we received from the government, so we're talking about non-dilutive funding for more than $10 million across the years that we've been basically using to develop the solution. What we're doing is basically trying to build the first pilot. And we're targeting specifically private 5G, the market, because that's, as I said, it's going to be the early adopter of the private 5G of the Open RAN paradigm. And this will give us the opportunity to demonstrate the technology, which is already a prototype. As we've shown, like we actually have a solution that is working. And this will give us the opportunity to raise funds. The funds will be used primarily to increase the team, specifically focusing on the software engineering part so that we can scale and advance the technology. This will give us the opportunity to start scaling up and go into start looking into the market of greenfield operators, because these will be the operators that will be starting using Open RAN ahead of time. And this will basically give us the path towards commercialization. And if you're more interested in all the details about how Z-Touch operates, how Z-Touch looks like, and how it's easy to control a 5G network using the AI that we have developed and all the intelligence to orchestrate the AI, you can stop by. We have a poster. We also have a demo. And if any question, you can also email us and interact offline. Thank you.
Hello, everyone. Can you hear me? My name is Hussam Abdulatif. I'm a third-year PhD student here at Northeastern. Today, I'm very excited to pitch to you guys Terranova, a startup with the vision to reach terabits per second wireless point-to-point backhaul links. So Terranova began as a research project within the Institute, supported by the Air Force Research Laboratories. And our group mainly focuses on unlocking the terahertz frequency band for ultra broadband communication. And we focus on solving the many challenges and obstacles in the terahertz frequency band to be able to communicate at ultra high speeds and low latencies. And some of those challenges present themselves whether they're in the electronics, channel characteristics, or even signal processing techniques. Within that group, I have been working on a specific subset of that research in which I was working on developing a communication platform that can access the terahertz frequency band and communicate over multi-gigahertz of bandwidth. This project began back in 2019, and within 3 years, we have been successful in developing a working prototype that consists of both hardware and software that communicates at the terahertz or sub-terahertz frequency band and communicates over 8 gigahertz of bandwidth. And we quickly realized that the solution we came up with was one of a kind and truly innovative, especially given its low cost and low power consumption, its high reconfigurability capabilities, and the fact that it can be easily deployable in the next few years. And with that in mind, we went ahead and we submitted a patent on this technology and began the commercialization process of this technology. So when it comes to our solution in particular, we envision our solution to be able to reach around 100 gigabits per second in the next year or so. That's wireless speeds. And be able to communicate to up to 500 meters in terms of communication distance while keeping the cost at under $10,000 per radio. Our main customers will be internet service providers, and we'll be competing with existing solutions such as fiber optics or millimeter wave wireless solutions. Some of those solutions might not be the most practical when it comes to specific circumstances, such, for example, extending coverage to rural areas or in 5G small cell deployment where there's a huge amount of 5G base stations being deployed, and fiber optics cannot be the most practical solution to connect all those 5G base stations. It is expected by 2026 that the backhaul connectivity market should be able to reach around $15.5 billion, and we're confident that we can tap into that market and compete with the existing fiber optics or millimeter wave solutions. In terms of commercialization process, we have been successful in securing 4 patents. 2 are pending at the moment, so in total we have around 6 patents. We're in the second stage or second round of interviews with Mass Challenge and Accelerator here in Massachusetts. We have also conducted different demos in different venues, such as the FRL workshop, IEEE Infocom conference, and the 6G symposium in DC. And we're almost done with company registration, which will help us in our next steps. So part of the next steps is licensing some of our software solutions with research and industry partners, such that we can gain more traction and generate a steady income revenue that will allow us to grow and hire more people to work on some of the performance metrics that we're trying to improve to meet the demands of existing solutions, such as increasing the distance and coverage, and work on upper networking protocols that have a huge opportunity for upcoming solutions and IPs. If you're interested in learning more, we do have a poster after this presentation, and I'll be more than happy to answer any of your questions. Thank you.
Hi everyone, my name is Yusuf Naderi. I'm excited to talk about commercialization work that we are doing as a part of Deep Charge with Kaushik Chaudhary and also Ufuk Munkuk here. Imagine a world free from wire and dead batteries. Picture a reality that you can easily charge your devices by just setting them on any surface. At Deep Charge, we are not only imagining this, we are actually bringing this to the life. We have developed the next generation of wireless energy infrastructure that not only is a technological advancement, but it is a paradigm shift. It is open, secure, sustainable, connected, and all above highly efficient. And I'd like to talk about the story here. Do we have the, where is the, there. Yes. Okay, good. Great. So our story and journey started at Genesis Lab, next generation network and system lab here at Northeastern, where we dream about a world that we can transfer energy over the distance. And we made it happen. This sparked our first breakthrough, which was distributed RF-based energy beamforming. Then we actually listen, learn, and pivot by talking with the customer and observing the market over the time. And our experience led us to basically do an exciting pivot, which going toward the magnetic resonance-based energy delivery, a software-based magnetic resonance energy delivery, which we found is a sweet spot to solve the real problem of a real customer. And throughout this journey, we basically have laid out the groundwork of about 9 family of the patents, which each of them is a step forward to realizing our vision. So let's talk about problem. Today, when we look at the energy infrastructure and device charging solution, there are 3 categories of the problem that persist. First, the existing solutions are just ineffective. From portable battery to adapter to a Qi wireless charger, this solution brings frustration, inconvenient, low charging speed, and limited mobility every day to all of us. And I think all of us resonate with that. But that's not the whole problem. There is the current solution, second, is they are disconnected. We have these individual units, chargers, adapters, that they are working independently together. That lead to lack and poor energy monitoring and management, lack of energy optimization, and also very high cost of the maintenance of this system. Let's talk about sustainability. The existing solutions are unsustainable. Looking at the one example, this is an adapter that all of us working. This adapter generates significantly electronic waste that result also to the carbon emission. The other big issue is that the best Silicon Valley adapter, they have an 85% efficiency, which means that we are losing 15% efficiency per adapter. And now the number of devices, just you multiply. This is a huge energy and unsustainable way to do it. So how to solve this? Actually, to solve this problem, we needed to come with a multidisciplinary solution that bring the best advanced state-of-the-art in wireless communication, IoT, power electronic, and machine learning. So let me tell you how the system works. We have created intelligent module that I have here, and actually I would invite you to come and see basically the demo. The energy tile, these are a different module. They easily install on their existing infrastructure and surface. They create a network together. They intelligently sense and charge devices, any type of devices over the surface. We charge all of the existing common off-the-shelf devices, from monitor to laptop to tablet to phone. But the software is as important as the hardware here. We do an energy optimization. We do basically energy monitoring and delivery, and provide the API access for other systems to integrate. So this is very important for seamless integration. We decided to go in a very unique go-to-market strategy. We're working with the currently value-added reseller and furniture company to integrate this technology into the existing furniture. And we have signed a strategic partnership and deployed our system in a multiple location, and actually recently have to sign MOU of more than 8.7 mil committed sales from our customer. Even we start looking at higher education workspace and high-tech enterprise workspace. So these are our niche targets. But we are excited about the next step of opportunity that goes beyond enterprise. We are talking about commercial spaces, public spaces, and residential. But that's not all what we're looking. The real game-changing story is for EV charging. the same infrastructure can be on a floor and enable EV to be in wirelessly charged. We actually already submitted a patent for that and started this journey. To industry partner, we believe the future of energy infrastructure is wireless. So you don't want to fall behind this. To prospective investor, if you care about planet, to persisting the planet, to enhancing energy efficient infrastructure and advancing the innovation, we like to talk to you. Thank you very much.
Hello, can you hear me well? Hello, this is Emre Can Demirörs. I'm a research assistant professor here at the WIoT Institute and co-founder of HydroNet. So HydroNet is the company that's focusing on bringing the internet underwater and empower it with AI-driven software-defined technologies. And I will tell you why this is important and what would be the implications of such technology. The problem that we're trying to solve today, if you want to connect devices in underwater, and assuming that you don't want to use cables, which could be time-consuming and expensive, then you have a problem. Because the radio frequency waves that we are using in our daily lives in Wi-Fi, Bluetooth, 5G, they're not working in underwater because radio frequency waves are absorbed by the water. And it's just the physics. Today, because of that, our seas and the oceans, which constitute 71% of the surface of our Earth, is unconnected or mostly unobservable. Today, there is no 21st century wireless underwater internet. There is no software-defined modems in underwater. And most of the technology today is constrained by the speed, range, and the reliability of the existing technology. So in a sense, we are unable to sense, monitor, or collect data in real time and make intelligent decisions based on that. As a consequence, what we are missing in underwater is that we are missing this interface between the digital world and the oceans, which in terrestrial environment, we call it Internet of Things. So today, we cannot talk about Internet of Things in underwater. To address that, what we're building is a software-defined underwater networking technology, which is using optical, ultrasonic, and acoustic waves to realize Wi-Fi and mesh-like networks in a plug-and-play fashion in underwater. This is our basic building block that is a fully programmable in-water communication, in-water sensing, and in-water AI processing module that we call it HydroNet modem. But as I was telling, we're not only building a modem and a point-to-point technology, but we are building a holistic networking technology. So we can actually create what you can call a underwater Wi-Fi on the left-hand side. We can create mesh-like networks to connect devices in a plug-and-play fashion. And we can also support high data rate links in underwater to create links that can stream video, which is not possible with today's technology. And by the way, this is just not a research anymore. It's actually working. We have tested in swimming pools, we have tested in Boston Harbor Marina, and we have tested in the Narragansett Bay with Naval Warfare Center at Newport. We have just concluded a DARPA SPR Phase 2 program, and we were successfully completed that program that we were invited to do a demonstration in the US Navy exercise in Trident Spectre, where we have actually shown a video streaming from the bottom of the ocean to the surface of the ocean. And actually, I have a short video here that is from that recording that is in Boston Harbor, that is streaming a video from the bottom of the ocean to a surface node. And besides that, we have a pet fish here that is living right next to our modems all the time. This was streamed to the YouTube. And actually, right now, we have an active link here that you can see it on my phone that is streaming from the bottom of the Boston Harbor. So this is basically, we can bring data from anywhere in the ocean to the fingertips in your phone that is connected anywhere. And this is actually gonna create that Internet of Things for underwater. But why this is important? What are the markets that can get impacted and we can actually be an enabler for? Obviously, as the internet created many new applications that nobody could conceive before, we believe HydroNet will create a lot of different enabling technologies for blue market economy. Some of them are including environmental monitoring, offshore equipment monitoring, that could be wind farms or oil pipelines, aquaculture, which there is a huge seafood deficit of US that is around 70 billion that we can address it with data-driven aquaculture. There is a huge and growing market in defense in underwater vehicles, and there is smart ports and shipyards that HydroNet technology can be an enabler. Overall, before I would like to wrap it up, I will tell you a little bit about what is on the horizon. So we are about to get another DARPA program, another in continuation SPR. We are currently also in talks with VCs for Series A funding. And we are about to also offer our first product line available to the public in the next few months, that we will be selling the modems and different products to the public, which we have already been selling to some private investigators and different research labs. Thank you very much.
Thank you to all. Oops, I guess I don't have the. Is this on? Okay. Thank you to all of the presenters. That's again, as I said, represents a lot of effort by people who already have a day job. All right. So we have Tommaso. Can you join? So this is the first year we're going to be presenting an Entrepreneur of the Year award. Because it's the first year, we had too much trouble identifying just a single recipient. So there's actually going to be two that will be given. And if the people could come up here, congratulations. Actually, hold on, I missed one thing. It's dedicated for their time and energy to the success and the startup and bringing the WIoT research to solving the problem and impacting society. This is a really nice award and very much appreciated.
Should probably say the names.
So the names are Professor Amirkan Demirers and Professor Yusuf Nadiri. I think they want to take a picture with each person.
Thank you. This one is for Yusuf. Thank you. And this is for Emre Can.
All right, thank you very much. So this is the end of the session on entrepreneurship, and I know we're heading into the poster session. Please, let's go over there. Let's spend time, give lots of feedback if you're industry to the researchers, because your feedback on real-world applications could be very valuable, and vice versa. Researchers, please give lots and lots of information to industry. Thank you very much.